In the first trillionth of a second after the Big Bang, the universe was a roiling inferno of energy and matter crushed into a space smaller than an atom. Temperatures soared beyond anything we can replicate in laboratories, and the laws of physics operated at their most extreme limits. In that unimaginable chaos, something impossible might have happened. Tiny pockets of space, denser than anything that would exist for billions of years to come, could have collapsed in on themselves, forming black holes no bigger than atoms, but containing the mass of mountains. These objects, if they exist, are called primordial black holes, and they weren't born from dying stars like the black holes we know today. They were born from the violence of creation itself. For decades, primordial black holes were treated as a mathematical curiosity, a footnote in cosmology papers that no one took seriously. But recently, something changed. New observations, unexplained mysteries, and mounting evidence have forced scientists to reconsider. Could these ancient relics be hiding in plain sight? Could they be the dark matter that holds galaxies together? Could they explain gravitational wave signals that don't match anything we predicted? The more we look, the more primordial black holes seem to challenge everything we thought we understood about the universe's birth, evolution, and fate. When the universe was small enough to hold. The Big Bang wasn't an explosion in space. It was an explosion of space itself. In the beginning, there was no universe to speak of, no galaxies, no stars, no atoms, not even empty space as we understand it. Everything that exists today, every particle, every photon, every bit of dark matter, was compressed into a point of infinite density. Then, roughly 13.8 billion years ago, that point began expanding, not outward into something, but expanding to become something. Space itself unfurled, carrying matter and energy along with it, like ink spreading on wet paper. The first moments were nothing like the universe we see now. At 1 second after the Big Bang, the temperature was about 10 billion degrees, hotter than the core of any star that would ever exist. At that point, protons and neutrons hadn't even formed yet. The universe was a soup of quarks and gluons, fundamental particles colliding at speeds approaching light, creating and annihilating each other in an endless cascade. Photons, the particles of light, were trapped in this chaos, unable to travel more than a fraction of a millimeter before smashing into something else. The universe was opaque, a blinding fog where light couldn't escape. As space expanded, it cooled. By the time the universe was 3 minutes old, temperatures had dropped enough for protons and neutrons to stick together, forming the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium. This period, known as Big Bang nucleosynthesis, lasted only about 17 minutes. In that brief window, the fundamental composition of matter in the universe was determined. Roughly 3/4 hydrogen, 1/4 helium. That ratio would hold for billions of years, shaping the chemistry of every star, planet, and gas cloud that would ever form. But before nucleosynthesis, in those first fractions of a second, the universe went through an even stranger phase. Between 10 to the negative 43 seconds and 10 to the negative 32 seconds after the Big Bang, space itself underwent a period of exponential expansion called inflation. In less time than it takes light to cross the width of a proton, the universe doubled in size at least 60 times. That's not just fast. It's faster than the speed of light, which is allowed because space itself was expanding, not objects moving through space. Inflation smoothed out irregularities, stretched quantum fluctuations into macroscopic structures, and set the stage for everything that came after. Inflation also did something crucial. It created tiny ripples in the density of space. Some regions ended up slightly more dense than others by amounts almost too small to measure. These density variations were the seeds of structure in the universe. Billions of years later, those ripples would grow into galaxies, clusters, and the vast cosmic web we observe today. But in the earliest moments, they were just quantum fluctuations blown up to cosmic scales, imperfections in an otherwise smooth universe. Here's where primordial black holes enter the picture. If inflation didn't smooth everything perfectly, If some regions were compressed just a bit too much, those overdense pockets could have collapsed under their own gravity. Normally, gravity is weak compared to other forces, especially in the chaotic environment of the early universe. But if the density contrast was large enough, gravity could win. A region of space might pinch off from the rest of the universe, collapsing into a black hole before the surrounding matter had time to react. These black holes would form not from stars, but from pure gravitational collapse in the primordial plasma. The timing mattered immensely. Primordial black holes could only form in a narrow window of opportunity. Too early, and the universe was still governed by quantum effects and inflation's exponential expansion. Too late, and the universe had expanded and cooled too much for overdensities to collapse. The sweet spot was roughly between 10 to the negative 30 seconds and 1 second after the Big Bang. In that interval, if conditions were right, black holes could freeze out of the cosmic fireball like ice crystals forming in supercooled water. The masses of these primordial black holes would depend on the size of the collapsing region. A collapse at 10 to the negative 23 seconds would create a black hole with the mass of about 1 kilogram, tiny by black hole standards, but still an object where the laws of quantum mechanics and general relativity collide. A collapse at 1 second would produce a black hole roughly 30 times the mass of the Sun. In between, there was room for an entire spectrum of masses: mountain mass black holes, asteroid mass black holes, planetary mass black holes, each one corresponding to a specific moment in cosmic history when the conditions were just right. The physics of formation was elegant but unforgiving. For a primordial black hole to form, the density contrast in a given region had to exceed a critical threshold. If the overdensity was 40% or more compared to the surrounding space, collapse was inevitable. Anything less, and radiation pressure or cosmic expansion would disperse the material before gravity could take hold. This threshold meant primordial black holes required extreme conditions, not just any wrinkle in spacetime would do. The fluctuations had to be rare and violent. One of the strangest aspects of primordial black holes is their size-to-mass ratio. A black hole with the mass of Earth would be about 9 millimeters across, the size of a marble. A black hole with the mass of an asteroid might be no larger than a single atom. Yet, despite their tiny dimensions, these objects would warp spacetime around them with terrifying efficiency. Anything that ventured within their event horizon, the point of no return, would be trapped forever. Not even light could escape. In the chaos of the early universe, these miniature monsters could have formed by the trillions, each one a gravitational trap lurking in the expanding cosmos. But here's the problem. We've never directly observed a primordial black hole. Not one. Every black hole we've detected so far, whether through X-rays from accretion disks, gravitational waves from mergers, or the shadows cast against glowing gas, has been a stellar mass or supermassive black hole formed from collapsing stars or galactic processes. Primordial black holes, if they exist, have left no obvious fingerprints. They're ghosts in the data, theoretical entities that might solve some of our biggest mysteries, or might not exist at all. Yet the case for them grows stronger with each new puzzle. Why does dark matter behave the way it does? Why do we detect gravitational waves from black hole mergers that seem too massive or too frequent? Why are the oldest quasars powered by black holes that formed impossibly fast after the Big Bang? Primordial black holes offer answers, but only if they're real. And proving they're real means going back to the beginning, to that first fraction of a second, and understanding a universe far more violent and strange than we ever imagined. The mass spectrum that shouldn't exist. Primordial black holes come in sizes that break every rule we know about black hole formation. When a massive star collapses, it produces a black hole with a predictable mass range, usually between 5 and 100 times the mass of the Sun. Supermassive black holes, the giants at the centers of galaxies, weigh millions or billions of solar masses. These categories make sense. We understand the astrophysical processes that create them. Primordial black holes, however, could span a mass range so vast it defies intuition, from microscopic black holes lighter than a snowflake to giants heavier than 1,000 suns. No other process in nature produces such diversity. The smallest primordial black holes would have formed in the earliest moments after the Big Bang, when the universe was densest and hottest. A black hole that formed at around 10 to the negative 23 seconds would have a mass of about 10 to the 15th grams, roughly the mass of a large mountain or a small asteroid. Its event horizon would be smaller than a single proton. These ultra-light primordial black holes are the most exotic, and they come with a strange property: they evaporate. Stephen Hawking predicted in the 1970s that black holes aren't entirely black. Quantum effects near the event horizon cause them to emit radiation, slowly losing mass over time. The smaller the black hole, the faster it radiates. A mountain mass black hole would evaporate completely in about 100 billion years. Any primordial black hole lighter than this would have already disappeared by now, exploding in a final burst of gamma rays sometime in the universe's past. This evaporation cutoff is crucial. If primordial black holes lighter than 10 to the 15th grams once existed, they're gone now, their brief lives ending in flashes of high-energy radiation. Searches for these bursts have turned up nothing conclusive, which either means such light black holes never formed in large numbers, or they're so rare we haven't caught one yet. But the absence of evidence isn't evidence of absence. It just narrows the window. The next mass range sits between asteroid mass and planetary mass black holes, roughly 10 to the 15th to 10 to the 25 grams. These are stable against Hawking radiation over the current age of the universe. They formed slightly later when the cosmos was a bit older and cooler, around 10 to the negative 10 seconds to 10 to the negative 5 seconds after the Big Bang. A black hole with the mass of Earth, for instance, would be the size of a ping-pong ball. A Mars mass black hole would fit in your hand. Their gravitational fields would be brutal up close, but from a distance, they'd behave like any other massive object, bending light and pulling on nearby matter. This intermediate mass range is where things get interesting. Planetary mass primordial black holes are heavy enough to act as dark matter candidates. They don't emit light, don't interact with electromagnetic radiation except through gravity, and they're incredibly difficult to detect directly. If a significant fraction of dark matter is actually made of these black holes, it would solve one of cosmology's biggest mysteries without requiring exotic new particles. It would also explain why dark matter seems to cluster the way it does, forming halos around galaxies and shaping the large-scale structure of the universe. Primordial black holes would naturally clump under gravity, mimicking the behavior we attribute to dark matter. Then there's the heavy end of the spectrum, black holes with masses comparable to or greater than the Sun. These would have formed around 1 second after the Big Bang, when the universe had cooled enough for larger overdensities to collapse. Stellar mass primordial black holes would be indistinguishable from those formed by dying stars. Same mass, same gravitational signature. But their origins would be radically different. Instead of being born in supernova explosions, they'd be fossils from the Big Bang itself, relics frozen in time from the first moment of creation. The heaviest primordial black holes could reach thousands of solar masses or more. These monsters might explain the intermediate mass black holes astronomers have struggled to understand. Objects too heavy to come from single-star collapses, but too light to be traditional supermassive black holes. Observations have found a few of these oddballs, lurking in globular clusters or detected through gravitational waves. Their existence doesn't fit neatly into standard black hole formation theories. But if they're primordial, formed in the densest regions of the early universe, the mystery evaporates. They're not anomalies, they're ancient. One of the strangest predictions is that the mass spectrum of primordial black holes might not be smooth. Instead, it could have peaks and valleys, clusters of preferred masses determined by the dynamics of the early universe. If inflation produced density fluctuations with specific patterns, say, more pronounced at certain scales, Then primordial black holes would form preferentially at corresponding masses. Imagine a population where most black holes are around 30 solar masses, with far fewer at 10 or 100. That kind of clustering would show up in gravitational wave detections, creating a fingerprint that doesn't match star formation models. Astronomers have started looking for exactly that signature. When LIGO and Virgo detect black hole mergers, they measure the masses of the objects involved. Most mergers so far involve black holes between 10 and 50 solar masses, consistent with stellar origins. But a few outliers exist, mergers where the black holes are unexpectedly heavy or where their mass ratio is unusual. Some of these could be primordial black holes colliding. Events that have been waiting to happen since the early universe. The statistics are still too limited to say for sure, but the pattern is tantalizing. The mass spectrum also determines how primordial black holes interact with their environment. Light ones would pass through ordinary matter almost unnoticed, too small to capture gas or dust efficiently. Heavy ones would accrete material aggressively, glowing as matter spirals into their event horizons. Intermediate ones would sit in between, occasionally flaring up if they wandered through a dense cloud, but otherwise staying dark. This range of behaviors makes primordial black holes both hard to detect and incredibly versatile as an explanation for multiple phenomena. But the mass spectrum creates a puzzle. If primordial black holes formed from density fluctuations, why don't we see more of them? Inflation smoothed the universe to extraordinary precision. Variations in density are only about 1 part in 100,000. For primordial black holes to form in abundance, those variations would need to be much larger in specific regions, by factors of hundreds or thousands. That requires fine-tuning the conditions during inflation in ways that aren't naturally predicted by standard models. Either something unusual happened during inflation, or primordial black holes are far rarer than we hope. Some researchers propose that phase transitions in the early universe could amplify density fluctuations locally, creating hotspots where primordial black holes were more likely to form. Others suggest that inflation wasn't perfectly smooth, that quantum fluctuations occasionally produced wild spikes in density that standard calculations underestimate. These ideas push the boundaries of established physics, venturing into territory where theory outpaces observation. Yet they're necessary if we want primordial black holes to be more than a mathematical curiosity. The mass spectrum of primordial black holes is a window into the universe's earliest moments, a fossil record written in gravity. Each mass range corresponds to a different epoch, a different set of conditions, a different chapter in cosmic history. If we could measure that spectrum precisely, if we could say definitively how many primordial black holes exist at each mass, we'd learn more about the Big Bang than from almost any other observation. We'd see the fingerprints of inflation, the texture of spacetime, the seeds of structure formation. But getting that measurement requires detecting primordial black holes first, and that's where the real challenge begins. The dark matter that might be hiding in plain sight. Dark matter is everywhere, yet we've never touched it, seen it, or directly measured it. It doesn't emit light, doesn't absorb light, and doesn't interact with electromagnetic radiation in any detectable way. We know it exists only through its gravitational effects. Galaxies spin too fast to be held together by visible matter alone. Galaxy clusters bend light from distant objects in ways that require far more mass than we can see. The large-scale structure of the universe, the cosmic web of filaments and voids, couldn't have formed without a dominant component of invisible matter. Roughly 85% of all matter in the universe is dark matter. The problem is, we don't know what it is. For decades, the leading candidates have been exotic particles, WIMPs, or weakly interacting massive particles that float through the universe like ghosts, barely touching ordinary matter. Physicists have built detectors, deep underground, shielded from cosmic rays, waiting for a WIMP to collide with an atomic nucleus. So far, nothing. Experiments have ruled out large swathes of parameter space where WIMPs were supposed to hide. Alternate particle candidates, like axions or sterile neutrinos, face similar challenges. Despite decades of searching, we haven't found a single dark matter particle. The silence is deafening. This is where primordial black holes step in as an alternative. What if dark matter isn't a new particle at all? What if it's something we already understand, black holes, but formed under conditions we haven't fully appreciated? Primordial black holes would act exactly like dark matter. They're invisible, they don't interact with light, and they only affect their surroundings through gravity. If a significant fraction of dark matter consists of these ancient black holes, it would explain the gravitational anomalies without invoking unknown physics. The idea isn't new. In the 1970s, Stephen Hawking and others floated the possibility that primordial black holes could be dark matter. But back then, constraints were loose and observations were limited. The proposal faded into the background as particle dark matter took center stage. In recent years, however, primordial black holes have roared back into contention. New data from gravitational wave observatories, improved models of the early universe, and the continued failure to detect particle dark matter have breathed new life into the hypothesis. Maybe we've been looking for the wrong thing all along. One of the strongest arguments for primordial black holes as dark matter comes from their mass range. If most primordial black holes have masses between 10 and 100 times the Sun, they'd cluster in galaxies just like dark matter is observed to do. Simulations of galaxy formation rely on dark matter halos, vast diffuse clouds of invisible matter that provide the gravitational scaffolding for galaxies to form. Replace the particle dark matter in those simulations with primordial black holes of the right mass, and the results are nearly indistinguishable. Galaxies still form, stars still ignite, and the cosmic web still takes shape. But the details matter. Primordial black holes don't behave exactly like particle dark matter. Particles move smoothly through space, colliding rarely if at all. Primordial black holes, on the other hand, are point masses. They can interact more strongly with each other through gravitational encounters, exchanging energy and momentum. In dense environments like the centers of galaxies, these interactions could alter the distribution of dark matter, creating subtle differences that might show up in observations. If we look closely enough, we might find that dark matter doesn't quite behave like particles should, and that mismatch could be the smoking gun for primordial black holes. Gravitational lensing offers another test. When light from a distant galaxy passes near a massive object, the object's gravity bends the light, distorting the image we see. This effect, predicted by Einstein's general relativity, is well established and routinely observed. Dark matter lenses light all the time, creating arcs and rings around galaxy clusters. But if dark matter is made of primordial black holes, the lensing would have additional features. A primordial black hole passing in front of a distant star would cause a brief, sharp spike in brightness, a micro-lensing event lasting hours to months, depending on the black hole's mass and speed. Astronomers have been searching for these events for years. The results are mixed. Surveys have detected micro-lensing events that could be caused by primordial black holes, but they could also be caused by ordinary stars, brown dwarfs, or rogue planets drifting through space. Distinguishing between these possibilities is difficult. A single event doesn't tell you much. You need statistics, large samples, patterns. Some studies claim the data rules out primordial black holes in certain mass ranges. Others argue the constraints are weaker than they seem, that primordial black holes could still make up a significant fraction of dark matter if they cluster in specific ways or have a particular mass distribution. One compelling clue comes from the rate of micro-lensing events toward the Magellanic Clouds, two small galaxies orbiting the Milky Way. The Macho project in the 1990s detected more lensing events than expected, suggesting there might be a population of massive compact objects in the halo of our galaxy. The masses inferred from these events were around half a solar mass, right in the range where primordial black holes could exist. Follow-up studies have been inconclusive, but the hint remains. If those lensing events were caused by primordial black holes, it would mean dark matter in the Milky Way includes a population of ancient black holes that have been orbiting our galaxy since before the first stars formed. Primordial black holes also offer a solution to the missing satellite problem. Simulations of dark matter predict that large galaxies like the Milky Way should have thousands of small satellite galaxies orbiting them. We only see a few dozen. This discrepancy has puzzled cosmologists for years. Maybe the simulations are wrong, or maybe something suppresses the formation of small galaxies. Primordial black holes could do that. If dark matter is made of black holes rather than particles, the dynamics of structure formation change. Small clumps of dark matter would be less stable, more prone to disruption. Fewer small galaxies would form, naturally matching what we observe. Then there's the question of when dark matter formed. In standard particle models, dark matter emerged gradually as the universe cooled, freezing out of the primordial plasma as interactions became too rare to maintain equilibrium. Primordial black holes, by contrast, would form suddenly in violent collapses during the first second of cosmic history. This difference has consequences for structure formation. Primordial black holes would start clustering earlier, seeding regions of space where galaxies would eventually grow. The timing could explain why the oldest galaxies seem to have formed faster than models predict. They had a head start, courtesy of black holes that were already there, waiting. Supermassive black holes present another puzzle. At the centers of most galaxies, including our own, lurks a black hole millions to billions of times the mass of the Sun. These giants somehow formed within the first billion years after the Big Bang, a time frame that seems impossibly short. Growing a supermassive black hole from scratch requires feeding it vast amounts of material continuously without interruption. Even under ideal conditions, it's hard to explain how these monsters got so big so fast. But if the seeds of supermassive black holes were primordial black holes, objects that started with masses of hundreds or thousands of suns, the problem becomes easier. You don't need to grow a black hole from nothing. You start with something substantial and let it accumulate more mass over time. Not everyone is convinced. Critics point out that primordial black holes would create problems of their own. If they're too abundant, they disrupt star formation, tearing apart molecular clouds before stars could ignite. If they're too massive, they'd overlens distant light sources, creating more distortions than we observe. If they cluster too strongly, they'd form dense cores in galaxies that don't match the smooth distributions we see. These constraints tighten the allowed parameter space, squeezing primordial black holes into narrower and narrower windows of possibility. Yet every time one window closes, another opens. New observations, new models, new ideas shift the boundaries of what's plausible. The search for dark matter has always been a process of elimination, ruling out possibilities one by one until only the truth remains. Primordial black holes are still in the game, and their appeal grows every year the particle searches come up empty. If dark matter really is hiding in plain sight, not as ghostly particles, but as ancient black holes forged in the fires of the Big Bang, it would be one of the greatest ironies in scientific history. We've been looking to the future, to new physics, when the answer was in the past all along. When quantum mechanics meets the event horizon. Black holes are where the universe breaks. At the event horizon, the boundary beyond which nothing escapes, space-time curves so sharply that time itself grinds to a halt for an outside observer. At the singularity, the infinitely dense point at the center, general relativity predicts that density and curvature become infinite, a mathematical catastrophe that signals the theory's failure. For decades, physicists have known that black holes are where quantum mechanics and general relativity collide, two pillars of modern physics that refuse to play nicely together. Primordial black holes make this conflict even worse. Stellar mass black holes form from collapsing stars, and their event horizons are large enough that quantum effects are negligible in most circumstances. A black hole 10 times the mass of the Sun has an event horizon about 60 kilometers across. At that scale, space-time looks smooth and classical physics dominates, but primordial black holes can be far smaller. A black hole with the mass of an asteroid might have an event horizon the size of an atom. At those scales, quantum mechanics can't be ignored. The smooth fabric of space-time predicted by general relativity dissolves into a froth of quantum fluctuations, and the rules change completely. Stephen Hawking was the first to realize that black holes aren't entirely black. In 1974, he showed that quantum effects near the event horizon cause black holes to emit radiation. Virtual particle pairs constantly pop into existence throughout space, a consequence of the Heisenberg uncertainty principle. Normally, these pairs annihilate almost instantly, but near a black hole's event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is radiating particles, Hawking radiation. The smaller the black hole, the hotter it radiates. A solar mass black hole emits radiation at a temperature of about 1/10 millionth of a Kelvin, negligible compared to the cosmic microwave background. But a primordial black hole with the mass of a mountain radiates at temperatures of billions of Kelvin, glowing brighter than the sun. This radiation comes at a cost. Every photon the black hole emits carries away energy, and by Einstein's mass-energy equivalence, energy loss means mass loss. Over time, the black hole shrinks. The smaller it gets, the hotter it radiates, and the faster it loses mass. The process accelerates, spiraling toward a dramatic end. A primordial black hole that started with the mass of a large asteroid would take trillions of years to evaporate completely. But in its final moments, it would explode in a burst of gamma rays and elementary particles, releasing energy equivalent to millions of nuclear bombs. No one has ever observed a primordial black hole exploding, but the predictions are clear enough that we've looked. Gamma ray observatories scan the sky for unexplained bursts that match the expected signature. So far, nothing definitive. Either primordial black holes are rarer than we hope, or they're not in the mass range where evaporation happens on timescales relevant to us. The absence of explosions sets limits on how many light primordial black holes could have formed in the early universe. If too many existed, we'd see their death throes scattered across the sky. Hawking radiation also creates a paradox. When a black hole evaporates, what happens to the information about the matter that fell in? In quantum mechanics, information is never destroyed. It's a fundamental principle. But if a black hole radiates purely thermally, with no trace of what fell in, the information seems to vanish. This is the black hole information paradox, one of the deepest puzzles in theoretical physics. Primordial black holes don't resolve the paradox, but they make it more urgent. If these objects formed in the early universe and are evaporating now, the question of where their information goes isn't abstract. It's happening in real time. Some researchers believe the solution lies in quantum gravity, a theory that unites general relativity and quantum mechanics. Such a theory doesn't exist yet, but its outlines are beginning to emerge. String theory, loop quantum gravity, and other approaches all predict that space-time at the smallest scales isn't smooth but granular, made of discrete units. Near the event horizon of a tiny primordial black hole, these quantum properties of spacetime would become important. The horizon itself might not be a sharp boundary, but a fuzzy region where quantum fluctuations dominate. Information might leak out gradually through these fluctuations, preserving unitarity without violating the no-hair theorem. Primordial black holes also test the limits of our understanding in another way, their formation mechanism. When a stellar black hole forms, there's a clear sequence of events. A massive star exhausts its nuclear fuel, the core collapses, and if the core is heavy enough, it becomes a black hole. The process is messy and violent, but it's governed by known physics, nuclear reactions, thermodynamics, hydrodynamics. Primordial black holes, by contrast, form from pure gravitational collapse in the early universe. There's no star, no nuclear fuel, no explosion, just space-time folding in on itself. The conditions are so extreme that the dividing line between classical and quantum physics blurs. In the first moments after the Big Bang, before primordial black holes could form, the universe was in a state called the quark-gluon plasma. Quarks and gluons, the building blocks of protons and neutrons, moved freely in a superhot, superdense soup. The physics of this state is governed by quantum chromodynamics, the theory of the strong nuclear force. When a region of this plasma collapsed to form a primordial black hole, it had to transition from a quantum-dominated state to a classical gravitational collapse. How exactly that happened is unclear. The equations of quantum chromodynamics are notoriously difficult to solve, especially under the conditions of the early universe. There's also the question of what happens inside a primordial black hole. General relativity predicts a singularity, but that prediction almost certainly breaks down. Quantum mechanics should prevent true infinities from appearing in nature. Some models suggest that inside a black hole, space-time doesn't collapse to a point, but instead bounces, creating a new expanding region, a baby universe. If primordial black holes behave this way, each one might be a gateway to another cosmos, forever sealed off from ours. It's a wild idea, impossible to test directly, but it underscores how little we understand about what's really going on beneath the event horizon. Primordial black holes also highlight a fundamental tension in cosmology. The Big Bang theory describes a universe that starts in a state of maximal entropy, disorder, and evolves toward increasing complexity. Structures like galaxies, stars, and planets represent local decreases in entropy, pockets of order carved out of chaos. Black holes, by contrast, are entropy maximized. A black hole has the highest entropy of any object with a given mass and volume, according to the laws of thermodynamics. When a primordial black hole forms in the early universe, it's creating a region of maximal entropy at a time when the universe as a whole is just beginning its journey toward complexity. It's entropy formation at the moment of creation. The interplay between quantum mechanics and gravity at the event horizon also affects how primordial black holes interact with their surroundings. A black hole isn't just a gravitational well, it's a thermodynamic object with a temperature and entropy. Hawking radiation means that black holes can exchange energy with the environment, heating nearby matter, or emitting particles that interact with cosmic radiation. For very small primordial black holes, these interactions might dominate over gravitational effects. A mountain mass black hole radiating at billions of Kelvin would be a brilliant source of high-energy particles, potentially detectable by space-based observatories if one happened to be nearby. Yet despite all the theoretical work, we have no direct evidence that Hawking radiation exists. It's never been observed, not even in analog systems designed to mimic black hole horizons. The effect is so weak for large black holes that it's swamped by other sources of radiation. Primordial black holes offer the best chance to test Hawking's prediction. If we could find one in the process of evaporating, measure its spectrum, and confirm that it matches the theoretical predictions, it would be a triumph for quantum field theory in curved spacetime. It would also prove that black holes aren't eternal, that even the most extreme objects in the universe have lifespans. The quantum nature of primordial black holes also complicates their role as dark matter. If they radiate, they lose mass, and their contribution to the total dark matter budget decreases over time. For most proposed dark matter candidates, the amount of dark matter remains constant. Primordial black holes don't have that luxury. Any population light enough to evaporate on cosmological timescales would be diminishing, gradually converting from mass into radiation. This makes them a less stable form of dark matter than particles, but it also makes them more interesting. They're not inert. They interact with the universe, even if only through Hawking radiation. At the intersection of quantum mechanics and the event horizon, primordial black holes become laboratories for physics we can't replicate anywhere else. They probe energy scales inaccessible to particle accelerators, test theories of quantum gravity under real conditions, and force us to confront the limits of our knowledge. If they exist, They're not just relics of the Big Bang. They're windows into the deepest mysteries of space-time itself. Gravitational waves and the echoes of ancient collisions. On September 14, 2015, the universe whispered to us, and for the first time, we heard it. Two black holes, each about 30 times the mass of the Sun, spiraled into each other at nearly the speed of light. In the final moments, they merged, releasing more energy in gravitational waves than all the stars in the visible universe were emitting in light at that instant. The signal lasted only a fifth of a second, a chirp that swept upward in frequency as the black holes accelerated toward their final embrace. LIGO, the Laser Interferometer Gravitational Wave Observatory, caught that chirp in two detectors separated by thousands of kilometers. It was humanity's first direct detection of gravitational waves, confirming a prediction Einstein made a century earlier. Since then, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Most fit expectations. Stellar mass black holes formed from dying stars, orbiting each other for millions or billions of years before finally colliding. But some don't fit the pattern. Some mergers involve black holes that are heavier than stellar collapse should produce, or they occur more frequently than star-based models predict, or the spins and orbital parameters don't match what we'd expect from stellar evolution. These anomalies have given primordial black holes a new lease on life. If some of the black holes LIGO detects aren't from stars, but from the Big Bang, it would explain the mismatches. Gravitational waves are ripples in spacetime itself, created whenever massive objects accelerate. When two black holes orbit each other, they stir spacetime like spoons in honey, sending waves radiating outward at the speed of light. These waves are incredibly weak by the time they reach Earth. LIGO's detectors measure distortions smaller than the width of a proton. But the principle is straightforward. The frequency and amplitude of the waves encode information about the masses, spins, and distances of the merging objects. By analyzing the waveform, astronomers can reconstruct what happened billions of light years away. The first hint that something was off came with the masses. Early LIGO detections included black holes around 30 solar masses, heavier than most models of stellar evolution predicted. Stars massive enough to produce such heavy black holes should lose significant mass through stellar winds before they collapse. The resulting black holes should be lighter, not heavier. Yet LIGO kept finding them. One explanation is that these black holes formed in environments with low metallicity, where stellar winds are weaker. Another is that they're not from stars at all, they're primordial. Primordial black holes wouldn't face the mass constraints that stellar black holes do. A primordial black hole's mass is determined by the conditions in the early universe, not by the life cycle of a star. If density fluctuations during inflation were large enough, primordial black holes could form with any mass in a wide range. 30 solar masses, 50 solar masses, even 100, all are possible. If a significant fraction of the black holes LIGO detects are primordial, it would explain why the mass distribution looks different from stellar predictions. The merger rate is another clue. LIGO detects black hole mergers at a rate that seems surprisingly high. For stellar black holes to merge, they need to form in binary systems, survive supernova explosions without being kicked apart, and spiral inward over billions of years due to gravitational wave emission. Each step has inefficiencies. The odds of two massive stars forming close together, both collapsing into black holes, and eventually merging are small. Yet LIGO sees mergers happening all the time. If primordial black holes are common, the rate makes more sense. They formed independently in the early universe, clustered together by gravity, and have been colliding ever since. No need for binary star evolution, just gravitational dynamics over cosmic timescales. Spins provide yet another test. When a star collapses to form a black hole, the rotation of the core gets amplified. The resulting black hole typically spins rapidly, with angular momentum aligned in a particular direction. If two black holes form in a binary system, their spins should be correlated with the orbital plane. LIGO has detected mergers where the spins seem misaligned or lower than expected. Primordial black holes wouldn't have this issue. They form from collapsing overdensities in the early universe, with no preferred spin direction. Their spins would be random, distributed evenly in all orientations. A population of merging primordial black holes would have a different spin distribution than stellar black holes, and that difference might already be showing up in the data. One particularly intriguing detection was GW190521, a merger that created a black hole about 150 solar masses. Both progenitors were in the so-called pair instability mass gap, a range where stars shouldn't be able to form black holes at all. Stars in this range undergo a runaway nuclear reaction that tears them apart before they can collapse. Yet here was a merger involving two objects in the forbidden zone. The simplest explanation is that they weren't from stars. They were primordial black holes, born in the early universe when the rules were different. The formation history also matters. Stellar black holes form continuously throughout cosmic history as stars evolve and die. Primordial black holes all formed in the first second after the Big Bang. This means their population was fixed from the start, while stellar black holes accumulated over billions of years. The merger rate for primordial black holes would be highest in the early universe when they were densest and would decline over time as they spread out. For stellar black holes, the rate increases over time as more stars die. By measuring how the merger rate changes with redshift, looking back in time, we can distinguish between these scenarios. Early results from LIGO and Virgo suggest the merger rate doesn't change much with redshift, or possibly decreases slightly going back in time. That's more consistent with primordial black holes than stellar ones. But the uncertainties are large, and the data is still limited. As detectors improve and we collect more events, the picture will sharpen. If the rate drops steeply at high redshift, primordial black holes become less likely. If it stays flat or increases, they gain ground. Gravitational waves also let us probe the environments where black holes merge. When two stellar black holes spiral together, they're often surrounded by gas and dust, material left over from the stars that formed them. This matter can interact with the black holes, emitting light in X-rays or other wavelengths. LIGO has looked for electromagnetic counterparts to black hole mergers and found none. That's surprising if the mergers involve stellar black holes in dense stellar environments, but it's exactly what you'd expect for primordial black holes. They formed long before stars existed, in regions devoid of gas. When they merge, there's nothing around them to light up. The absence of electromagnetic signals is circumstantial evidence that at least some LIGO detections might be primordial. The waveforms themselves could hold subtle clues. Numerical simulations of black hole mergers predict the exact shape of the gravitational wave signal based on the masses, spins, and orbital parameters. These predictions assume the black holes are isolated, with no surrounding matter or unusual properties. If primordial black holes have different internal structures, perhaps due to their formation mechanism, the waveforms might deviate slightly from expectations. So far, no deviations have been seen, but the precision of LIGO's measurements improves with every upgrade. Future detectors, like the Einstein telescope or Cosmic Explorer, will be sensitive enough to catch tiny anomalies that current instruments miss. One exotic possibility is that primordial black holes could merge multiple times. A black hole that forms from a merger is itself a black hole, capable of merging again. In dense clusters of primordial black holes, hierarchical mergers could be common. A 10 solar mass black hole merges with another 10 solar mass black hole to create a 20 solar mass object. That object later merges with a 30 solar mass black hole to create a 50 solar mass behemoth. Each generation of mergers produces heavier black holes with characteristic spin distributions. If LIGO detects black holes with spins that indicate their second or third generation mergers, it would be strong evidence for a dense population of primordial black holes in the early universe. The spatial distribution of mergers also matters. Stellar black holes form in galaxies, so their mergers should trace the distribution of galaxies across the sky. Primordial black holes, on the other hand, would be distributed more smoothly following the dark matter. If LIGO could map where black hole mergers are happening, whether they cluster around galaxies or spread evenly through space, it would provide another test. The challenge is that LIGO's ability to localize mergers is limited. Most detections pinpoint the source to a region spanning hundreds or thousands of square degrees on the sky. Future detectors with better angular resolution will help narrow this down. Another avenue is the stochastic gravitational wave background. Just as the cosmic microwave background is the faint afterglow of the Big Bang's light, there should be a gravitational wave background from all the unresolved mergers happening throughout the universe. LIGO is beginning to probe this background, and the signal's strength and frequency distribution depend on the population of merging black holes. If primordial black holes are abundant, they'd contribute to the background in a distinctive way, especially at higher frequencies where stellar black holes are less common. Pulsar timing arrays offer a complementary approach. These networks of ultra-precise clocks, millisecond pulses scattered across the galaxy, can detect gravitational waves at much lower frequencies than LIGO, sensitive to black hole mergers involving millions or billions of solar masses. If supermassive black holes grew from primordial seeds, pulsar timing arrays might catch their mergers, providing a direct link between the smallest primordial black holes and the largest structures in the universe. Gravitational waves have opened a new window on the cosmos, one that doesn't rely on light. Black holes can hide from telescopes, but they can't hide from detectors that measure space-time itself. Every merger LIGO detects is a piece of the puzzle, a data point constraining the population of black holes in the universe. As the catalog grows, patterns will emerge. Some will fit stellar models perfectly. Others will demand explanations that go beyond conventional astrophysics. And in those anomalies, primordial black holes might finally reveal themselves, ancient echoes of the Big Bang reverberating through space-time billions of years after their creation. The constraint paradox: why primordial black holes are almost allowed. Primordial black holes occupy a strange place in cosmology. Depending on how you look at the evidence, they're either everywhere or nowhere. The constraints from different observations pull in opposite directions, creating a tension that researchers struggle to resolve. Some measurements suggest primordial black holes can't make up more than a tiny fraction of dark matter. Others leave room for them to be the dominant component. Threading the needle between these limits requires careful assumptions and creative models, and the margins keep getting thinner. One of the strongest constraints comes from the cosmic microwave background, the faint glow of light from when the universe was only 380,000 years old. At that time, the universe transitioned from an opaque plasma to a transparent gas as electrons combined with protons to form neutral hydrogen. The photons released during this recombination have been traveling through space ever since, stretched by cosmic expansion into microwaves. Their distribution across the sky encodes a wealth of information about the early universe, its density, composition, temperature, and the seeds of structure that would grow into galaxies. If primordial black holes existed during recombination, they would have affected the cosmic microwave background. Black holes accrete matter, pulling in gas and heating it through friction. Even a small population of primordial black holes would inject energy into the surrounding plasma, ionizing hydrogen atoms and altering the recombination process. This would change the statistical properties of the microwave background, smoothing out small-scale fluctuations or shifting the power spectrum. Measurements from satellites like Planck are exquisitely sensitive to these effects, and they set tight limits on how many primordial black holes could have existed at that time. For black holes heavier than about 10 solar masses, the constraints are severe. If more than a few % of dark matter consisted of such black holes, their accretion would have left detectable imprints on the cosmic microwave background. The data shows no such imprints, which means either primordial black holes are rare in this mass range, or they accrete matter far less efficiently than expected. Some models suggest that primordial black holes formed in low-density regions where there was little gas to accrete, allowing them to stay dark and avoid detection. Others propose that feedback mechanisms, radiation pressure or magnetic fields, prevented efficient accretion. But these workarounds require fine-tuning the conditions in ways that feel contrived. Lighter primordial black holes face different constraints. Hawking radiation becomes relevant for masses below about 10 to the 17th grams, roughly the mass of a small moon. Black holes lighter than this would emit detectable gamma rays as they evaporate. Telescopes scanning the sky for gamma-ray bursts have found plenty of transient sources, but none match the predicted signature of an evaporating black hole. This rules out large populations of light primordial black holes, at least in the mass ranges where evaporation happens on timescales we can observe. Gravitational microlensing provides constraints across a broad range of masses. When a primordial black hole passes between Earth and a distant star, it acts as a gravitational lens, briefly magnifying the star's light. The duration and intensity of the lensing event depend on the black hole's mass. Surveys monitoring millions of stars have detected microlensing, but most events can be explained by ordinary stars or brown dwarfs. The lack of excess events rules out primordial black holes as the dominant form of dark matter in certain mass ranges, particularly around 1 to 10 solar masses. Yet these constraints aren't airtight. Microlensing surveys have limited coverage. They monitor specific regions of the sky, like the Magellanic Clouds or the galactic bulge, and extrapolate to the whole galaxy. If primordial black holes cluster in regions we haven't surveyed intensively, they could slip through the cracks. Their spatial distribution matters enormously. If they're evenly spread through the galaxy like a smooth, dark matter halo, the constraints are strong. If they clump into dense pockets, the constraints weaken because most lines of sight wouldn't intersect a clump. Dynamical constraints add another layer. Primordial black holes moving through dense stellar environments would interact gravitationally with stars, perturbing their orbits. Over time, these interactions would heat the stellar system, puffing it up like a soufflé. Globular clusters, ancient collections of stars tightly bound by gravity, are sensitive to this heating. Observations show that globular clusters remain compact, which limits how many primordial black holes can pass through them. If too many primordial black holes existed, globular clusters would have dissolved long ago. Wide binary stars provide a similar test. These are pairs of stars orbiting each other at large separations, sometimes thousands of astronomical units apart. Such wide binaries are fragile. A close encounter with a massive object can tear them apart. The survival of wide binaries in the Milky Way places limits on the number of massive primordial black holes wandering through the galaxy. Too many, and the binaries would be disrupted. The observed abundance of intact wide binaries suggests that primordial black holes heavier than a few tens of solar masses can't dominate the local dark matter. Then there's the issue of early structure formation. If primordial black holes were the seeds of the first galaxies, they would have started pulling in gas and forming stars very early in cosmic history. The oldest galaxies we observe are consistent with this picture, but they also constrain it. If primordial black holes were too abundant or too massive, they would have overseeded structure formation, creating more massive galaxies earlier than we see. The delicate balance required suggests that primordial black holes, if they exist, occupy a narrow sweet spot, common enough to matter, but not so common they dominate. On the flip side, some observations hint at more primordial black holes than constraints seem to allow. The abundance of intermediate mass black holes, the speed at which supermassive black holes grew, the rate of gravitational wave detections, all of these suggest a population of black holes that formed early and exists in larger numbers than standard models predict. Reconciling these hints with the constraints requires creativity. Maybe primordial black holes have an unusual mass distribution, clustered at specific values where constraints are weakest. Maybe they formed with high velocities, zipping through the galaxy too fast to leave gravitational traces. Maybe their formation mechanism involved physics we haven't accounted for, changing their properties in subtle but important ways. The tension extends to theoretical predictions. Calculating how many primordial black holes should form in the early universe depends on the statistical properties of density fluctuations during inflation. Inflation smoothed the universe to extraordinary precision, leaving fluctuations of only about 1 part in 100,000. For primordial black holes to form in significant numbers, those fluctuations need to be amplified locally, reaching levels of 1 part in a few. That's a huge amplification, and it doesn't happen in the simplest models of inflation. It requires special conditions, phase transitions, non-standard inflaton potentials, features in the inflationary dynamics. Each of these introduces free parameters that can be tuned to produce the right abundance of primordial black holes. Critics argue that this tuning is a weakness. If you need to invoke exotic physics to make primordial black holes abundant enough to matter, maybe they're not the answer. Proponents counter that invoking exotic particles for dark matter is no different. We've never detected a WIMP or an axion either, and those models also require fine-tuning their properties to fit observations. The playing field is more level than it appears. Another complication is that primordial black holes aren't a single thing. They're a population with a mass spectrum, a spatial distribution, and possibly a velocity distribution. Constraints that apply to one part of parameter space don't necessarily apply to others. A model where most primordial black holes are asteroid mass, with a smaller population of stellar mass objects, might evade all current limits. The challenge is finding a formation mechanism that produces such a distribution naturally, without ad hoc adjustments. The too much too little problem also reflects a deeper issue. We're trying to infer the properties of objects we've never directly observed based on their absence or subtle effects. It's like trying to deduce the shape of an invisible sculpture by measuring the shadows it casts under different lights. Each shadow, each constraint rules out certain shapes, but many possibilities remain. Until we detect a primordial black hole unambiguously, through a method that distinguishes it from ordinary black holes or other astrophysical objects, we're stuck in this liminal space where everything is possible but nothing is certain. What's needed is a smoking gun, an observation that can only be explained by primordial black holes and not by any other known astrophysical process. That could be a gravitational wave signal with a unique signature, a microlensing event with impossible properties, or a gamma-ray burst from an evaporating black hole. Until that happens, the debate will continue, with constraints tightening and models evolving in response. Primordial black holes will remain trapped between too much and too little, tantalizing but elusive. Inflation's wild fluctuations and the seeds of collapse. Inflation is one of the most successful theories in cosmology, yet it's also one of the most poorly understood. The core idea is simple. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size at least 60 times in less than 10 to the negative 30 seconds. This rapid growth solved several problems with the standard Big Bang model, including why the universe is so flat, so homogeneous, and so isotropic. But inflation isn't a single theory. It's a framework with dozens of variants, each making different predictions about the early universe. The mechanism driving inflation is thought to be a scalar field called the inflaton, a hypothetical entity that permeated all of space in the earliest moments. As the inflaton field rolled down its potential energy curve, it released energy that drove the exponential expansion. When the field reached the minimum of its potential, inflation ended, and the energy was converted into particles and radiation, a process called reheating. The universe transitioned from the inflationary epoch to the hot, dense state we associate with the traditional Big Bang. During inflation, quantum fluctuations in the inflaton field were stretched to macroscopic scales. These fluctuations became the seeds of structure in the universe, tiny variations in density that would eventually grow into galaxies and galaxy clusters. Most models of inflation predict that these fluctuations are small and nearly scale invariant, meaning they have the same amplitude at all size scales. observations of the cosmic microwave background confirm this prediction with remarkable precision. The fluctuations are about 1 part in 100,000, just as inflation predicted. But here's where primordial black holes enter the story. If inflation produced fluctuations that were slightly larger in certain regions or at certain scales, those overdense regions could collapse into black holes. The threshold is steep. A fluctuation needs to be about 40% denser than its surroundings to overcome radiation pressure and collapse. In standard inflation models, such large fluctuations are exponentially rare. The probability drops off so sharply that primordial black holes would be negligible, far too rare to explain dark matter or contribute to the black hole population we observe. Yet there's nothing in the fundamental physics of inflation that forbids larger fluctuations. The inflaton potential could have features, bumps, wiggles, or flat regions that temporarily slow the field's evolution. During these periods, quantum fluctuations would grow larger than usual, amplifying the density contrasts at specific scales. When the field resumed its rapid roll, inflation would continue normally, but the enhanced fluctuations would remain, frozen into the fabric of space-time. These regions would later collapse into primordial black holes, with masses corresponding to the scales where fluctuations were amplified. Different inflaton potentials predict different patterns of fluctuations. A potential with a single feature might produce primordial black holes clustered at one mass, say 30 solar masses. A potential with multiple features could produce several peaks in the mass spectrum. A potential with a rough, bumpy structure might generate black holes across a wide range of masses, creating a broad spectrum. The diversity of possibilities is both a strength and a weakness. It means inflation can accommodate primordial black holes, but it also means we can't make firm predictions without knowing the exact shape of the inflaton potential. One intriguing mechanism is ultra-slow roll inflation. In this scenario, the inflaton field enters a phase where its kinetic energy nearly vanishes, and it rolls extraordinarily slowly down the potential. During this phase, quantum fluctuations grow unchecked, reaching amplitudes orders of magnitude larger than in standard inflation. The slow roll phase is temporary. If it lasted too long, inflation would never end. But even a brief period is enough to generate the large fluctuations needed for primordial black hole formation. When the inflaton exits the slow roll phase and accelerates again, inflation continues, eventually ending normally. Ultra-slow roll inflation predicts a spike in the primordial power spectrum, the distribution of fluctuations across different scales. That spike would show up as an excess of structure formation at specific scales, possibly visible in the distribution of galaxies or the clustering of dark matter. So far, no such spike has been definitively detected, but the observations are challenging. Small-scale structure is difficult to measure, and the signal could be subtle, buried in the noise of galaxy formation and other astrophysical processes. Phase transitions in the early universe offer another route to primordial black holes. As the universe cooled, it underwent several phase transitions, similar to water freezing into ice. During these transitions, the vacuum state of various fields changed, releasing energy and creating bubbles of new phase surrounded by old phase. If the transition was first order, meaning it happened abruptly rather than gradually, the collisions between expanding bubbles could create regions of extreme density. These collision zones might collapse into primordial black holes, with masses determined by the energy scale of the phase transition. The QCD phase transition, when quarks and gluons bound together to form protons and neutrons, is a candidate for such an event. It occurred when the universe was about 10 microseconds old, at temperatures around 2 trillion Kelvin. The transition was likely a crossover rather than a first-order phase transition, but uncertainties remain. If the transition had a first-order component, even briefly, it could have produced primordial black holes with masses around a solar mass. These would sit right in the range where current constraints are weakest, and they'd be perfect candidates for the black holes LIGO detects. Cosmic strings, hypothetical one-dimensional defects in space-time, could also seed primordial black holes. These strings would form during phase transitions in the early universe, stretching across vast distances with immense tension. Loops of cosmic string could break off and collapse, their mass concentrating into a small volume. If the loop was dense enough, it would form a black hole. The masses of these black holes would depend on the length and tension of the string loops, potentially spanning a wide range. All of these mechanisms, features in the inflaton potential, ultra-slow roll phases, phase transitions, cosmic strings, are speculative. They extend the standard inflation framework in ways that haven't been confirmed observationally. But that's the nature of early universe physics. We're probing epochs and energy scales far beyond what we can access in laboratories, relying on theoretical consistency and indirect observations. Inflation itself was speculative when first proposed in the 1980s. It gained credibility because it made predictions that were later confirmed, like the flatness of the universe and the pattern of fluctuations in the cosmic microwave background. Primordial black holes offer a way to test inflation more rigorously. If we could measure the abundance and mass distribution of primordial black holes precisely, we'd be constraining the dynamics of the inflaton field during the first instance of cosmic history. Different formation mechanisms leave different fingerprints. A spike in the power spectrum at specific scales, a broad distribution of masses, a correlation between black hole abundance and large-scale structure. All of these would point back to the physics of inflation. The challenge is that inflation is versatile, almost too versatile. For nearly any observation, you can construct an inflaton potential that produces it. This makes inflation difficult to falsify, a point critics have raised repeatedly. Primordial black holes don't solve this problem, but they sharpen it. If primordial black holes exist in large numbers, it means inflation wasn't as simple as the minimal models suggest. It had features, complexities, dynamics that aren't captured by a smooth quadratic potential. That's valuable information, even if it doesn't single out one specific model. The wild fluctuations required for primordial black hole formation also raise questions about what else might have formed in the early universe. If density contrasts were large enough to make black holes, were there other exotic objects? Could topological defects like monopoles or domain walls have appeared in greater numbers than predicted? Could there be regions of the universe where inflation ended earlier or later, creating pocket universes with different properties? The implications ripple outwards, touching on the multiverse, the landscape of string theory, and the ultimate fate of the cosmos. At its core, the link between inflation and primordial black holes is about amplification. Inflation amplifies quantum fluctuations into classical density variations. Under the right circumstances, it can amplify them enough to form black holes. Understanding when, where, and how that amplification happens is one of the deepest questions in cosmology. Answer it, and we'll know not just whether primordial black holes exist, but what the first moments of the universe were really like. Probing dark matter with planetary orbital anomalies. If primordial black holes pervade the galaxy, some must pass near Earth. They'd be invisible, detected only through their gravitational influence. But if one happened to pass close enough through the solar system, perhaps even through the inner planets, the effects would be measurable. Astronomers have begun searching for these transits, looking for the subtle gravitational tugs that would betray a primordial black hole's presence. So far, the searches have come up empty, but they're just beginning, and the sensitivity improves with each new dataset. The solar system is a gravitational laboratory. The orbits of planets, moons, and asteroids are determined by the Sun's gravity and their mutual interactions. These orbits are predictable, measured with exquisite precision using radar ranging, spacecraft tracking, and observations of stellar occultations. Any additional mass passing through the system would perturb these orbits, shifting positions by tiny amounts. For a primordial black hole, The shift would depend on its mass, speed, and trajectory. A Mars-mass black hole passing through the inner solar system would tug on Earth's orbit, shifting its position by a few hundred meters, detectable with current technology. The search focuses on Mars because its orbit is tracked more precisely than any other planet. Spacecraft have orbited Mars continuously since the 1990s, using radio signals to measure distances accurate to within meters. If a massive object passed nearby, Mars would lurch slightly off its predicted path. The timing of the perturbation would reveal when the encounter happened, and the magnitude would constrain the object's mass. Researchers have analyzed decades of Mars tracking data, looking for unexplained shifts. So far, nothing stands out above the noise. Asteroids offer another avenue. The solar system contains millions of asteroids, most orbiting between Mars and Jupiter. Their orbits are less well known than planetary orbits, but for the brightest asteroids, the positions are tracked carefully. A close encounter with a primordial black hole would deflect an asteroid's path, causing it to arrive at a predicted position earlier or later than expected. By monitoring the largest asteroids over years, astronomers can search for these timing anomalies. The challenge is distinguishing primordial black hole encounters from other perturbations, gravitational interactions with planets, the Yarkovsky effect from uneven heating, or collisions with smaller asteroids. The outer solar system presents opportunities too. The orbits of distant trans-Neptunian objects, small icy bodies beyond Neptune's orbit, have peculiarities that some researchers attribute to an unseen massive object. The hypothetical Planet 9, if it exists, would be a super-Earth-sized world lurking in the outer reaches of the solar system. But what if Planet 9 isn't a planet at all? What if it's a primordial black hole, 5 to 10 times Earth's mass, orbiting the Sun at hundreds of astronomical units? Such an object would gravitationally shepherd trans-Neptunian objects the same way a planet would, explaining the orbital clustering without requiring a massive icy world. The idea is provocative, but difficult to test. A 5 Earth mass black hole would be about the size of a grapefruit, utterly invisible against the blackness of space. You couldn't spot it with a telescope, there's nothing to see, but it would accrete material from the sparse gas and dust in the outer solar system, heating that material and possibly emitting faint X-rays or radio waves. Searches with Chandra and other observatories have looked for such signatures in the regions where Planet 9 might hide. Nothing definitive has emerged, but the searches continue. Another possibility is that primordial black holes could explain some of the anomalies in spacecraft trajectories. When probes like Pioneer 10 and 11 traveled to the outer solar system and beyond, they experienced tiny, unexplained accelerations. The Pioneer anomaly, as it was called, puzzled scientists for years before being attributed to thermal radiation from the spacecraft pushing them slightly off course. But during the investigation, researchers considered other possibilities, including gravitational effects from unseen mass distributions in the solar system. Primordial black holes were among the candidates, though they were ruled out for the specific Pioneer anomaly. Still, the episode demonstrated how sensitive spacecraft tracking can be to small gravitational influences. Lunar laser ranging is one of the most precise measurements in the solar system. Reflectors placed on the Moon by Apollo astronauts allow scientists to bounce laser beams off the lunar surface and measure the round-trip time to within picoseconds. This tracks the Moon's orbit around Earth with millimeter precision. If a primordial black hole passed through the Earth-Moon system, the Moon's orbit would shift detectably. Decades of laser-ranging data constrain how often such encounters can happen. The limits aren't tight enough to rule out primordial black holes as dark matter, but they narrow the possibilities. The sensitivity of these searches depends on how fast primordial black holes move. If they're part of the galactic dark matter halo, they'd be traveling at a few hundred kilometers per second relative to the solar system. At those speeds, a close encounter would be brief, lasting days to weeks. The gravitational perturbation would be a transient blip in the data, requiring careful analysis to detect. if primordial black holes move slower, perhaps because they're clustered in a dense local population, the encounters would last longer and be easier to spot. There's also the possibility of direct impacts. A primordial black hole passing through a planet wouldn't stop. It would punch straight through, entering one side and exiting the other in a fraction of a second. The black hole's gravity would compress material along its path, creating a narrow channel of devastated rock or gas. For Earth, such an event would be catastrophic if the black hole passed through a densely populated region, but most of the planet would be unaffected. The black hole itself would be unscathed, gaining a tiny amount of mass from accreted material, but otherwise continuing on its trajectory. Could we detect such an event if it happened? Maybe. Seismometers would record the shockwave as the black hole tore through the planet. Satellites might detect unusual gravitational signals if they were close enough. If the black hole passed through the atmosphere, it would create a sonic boom and possibly a visible trail from ionized air. But the event would be over so quickly that most monitoring systems would miss it, recording only the aftermath. Searching historical records for unexplained seismic events or atmospheric phenomena might turn up candidates, though distinguishing them from natural events like earthquakes or meteorite impacts is nearly impossible. The Sun offers a unique detection opportunity. If a primordial black hole passed through the Sun, it would accrete solar material, briefly glowing as gas spiraled into its event horizon. The amount of accreted mass would depend on the black hole's size and speed. A small, fast-moving black hole might zip through the Sun without capturing much. A larger, slower one could cause a noticeable brightening, a transient flare lasting minutes to hours. Solar observatories constantly monitor the Sun for such anomalies, recording flares, coronal mass ejections, and other activity. A primordial black hole transit would have a distinctive signature, a localized brightening moving through the solar disk, unconnected to magnetic activity or sunspot regions. No such event has been reported, but the absence doesn't rule out primordial black holes. Transit events would be rare, happening perhaps once per century or less, depending on the local density of black holes. The Sun's surface is turbulent, filled with convective cells and magnetic structures that create their own transients. Distinguishing a primordial black hole from this background noise requires sophisticated analysis. Automated detection algorithms trained on known flare signatures might flag unusual events for closer inspection. Gravitational microlensing within the solar system is another approach. If a primordial black hole passed directly between Earth and a background star, it would lens the star's light, causing a brief brightening. The effect would be minuscule. Most primordial black holes are too light to produce strong lensing. But with enough stars monitored, a statistical signal might emerge. Some asteroid survey telescopes image the same regions of sky repeatedly, searching for moving objects. The same datasets could be mined for microlensing events, looking for stars that brighten and fade in patterns inconsistent with asteroids or planets. The solar system is vast, and space is mostly empty. Even if primordial black holes are common in the galaxy, the odds of one passing close to Earth are small, but they're not zero. Over the 4.5 billion-year history of the solar system, countless primordial black holes would have transited if they make up a significant fraction of dark matter. Some might have passed close to planets, disrupting orbits or ejecting moons. Others might have collided with asteroids, shattering them into fragments. The cumulative effects could be imprinted in the solar system structure, waiting for careful analysis to reveal them. One of the most exciting prospects is using the solar system as a detector for primordial black holes passing through nearby space, even if they don't enter the system itself. The gravitational influence of a massive object extends far beyond its physical size. A primordial black hole passing within a few astronomical units of the solar system would tug on the planets, creating correlated timing shifts across multiple worlds. By monitoring the entire solar system simultaneously, Earth, Mars, Jupiter, Saturn, researchers could triangulate the trajectory of a passing black hole, measuring its mass and velocity with high precision. This kind of solar system-scale astrometry is becoming feasible with modern technology. Space missions like Gaia are mapping the positions and motions of billions of stars with unprecedented accuracy. But the same techniques can be applied to solar system objects. Future missions might include dedicated monitors for transient gravitational signals, networks of spacecraft positioned throughout the system, each tracking nearby planets and asteroids. If a primordial black hole passed through, the network would detect it, providing the first direct observation of one of these elusive objects. The hunt for tiny monsters in our solar system is a long shot, but it's a hunt worth pursuing. Every negative result tightens the constraints on primordial black holes, narrowing the parameter space where they can hide. Every new dataset, planetary orbits, asteroid positions, spacecraft trajectories adds another piece to the puzzle. And if one day an unexplained perturbation appears in the data, something that can only be explained by a massive, invisible object passing through, it might be the discovery that changes everything. A primordial black hole, caught in the act, revealing itself at last. Supermassive seeds from the cosmic dawn. The most massive black holes in the universe appeared impossibly early, within the first billion years after the Big Bang, when the cosmos was still in its infancy. Quasars powered by billion solar mass black holes were already shining. These objects are among the brightest in the universe, outshining entire galaxies as matter spirals into their maws at tremendous rates. The problem is, black holes shouldn't grow that fast. Even under ideal conditions, feeding continuously and efficiently, a stellar mass black hole would take billions of years to reach such gigantic sizes. Yet, the quasars are there, blazing away in the cosmic dawn, demanding an explanation. The standard formation pathway for supermassive black holes starts with a massive star. The star collapses at the end of its life, forming a black hole of tens to perhaps 100 solar masses. That black hole settles into the center of a forming galaxy where gas is plentiful. It begins accreting, pulling in surrounding material and growing slowly. The accretion rate is limited by the Eddington limit. When matter falls into a black hole, it heats up and radiates, and that radiation exerts outward pressure. If the black hole tries to accrete too fast, the radiation pressure blows away the infalling material, choking off further growth. The Eddington limit means black holes grow exponentially, but slowly, doubling their mass every few tens of millions of years under optimal conditions. Starting from 100 solar masses, even with continuous Eddington-limited growth, it would take about 1 billion years to reach 1 billion solar masses. That's cutting it close. The earliest quasars are observed when the universe was only 600 to 700 million years old. For a black hole to grow that massive that quickly, it needs either a much larger starting mass or a way to exceed the Eddington limit. Both options are difficult to achieve with standard astrophysics. Primordial black holes solve the timing problem elegantly. If black holes with masses of thousands or even millions of solar masses formed directly in the early universe, they'd provide ready-made seeds for supermassive black holes. Start with a 10,000 solar mass primordial black hole, drop it into a gas-rich protogalaxy, and let it accrete. Even with modest growth rates, it could reach 1 billion solar masses within the available time. No need to push the Eddington limit. No need to invoke exotic accretion mechanisms. The heavy lifting was already done in the first second after the Big Bang. The formation of such massive primordial black holes requires extreme conditions. Density fluctuations during inflation would need to be enormous at the relevant scales, far larger than the fluctuations that seeded ordinary galaxies. This is possible if the inflaton potential had sharp features, or if phase transitions amplified fluctuations locally. The window of opportunity was narrow, too early, and the universe hadn't cooled enough, too late, and the fluctuations would be too small. But in that sweet spot, perhaps around 1 second after the Big Bang, regions of space massive enough to form intermediate mass black holes could collapse. Another mechanism involves direct collapse. In the standard picture, the first stars formed when primordial gas clouds, composed almost entirely of hydrogen and helium, cooled and fragmented into clumps. These clumps collapsed into stars, massive and short-lived, ending their lives as stellar black holes. But under certain conditions, a gas cloud might skip the star formation stage entirely. If the cloud was massive enough and couldn't cool efficiently, it would remain hot and stable until it reached a critical mass. Then it would collapse directly into a black hole, bypassing the stellar phase. This direct collapse scenario requires suppressing normal cooling mechanisms. Hydrogen molecules, which normally radiate away thermal energy and allow clouds to fragment, need to be destroyed or prevented from forming. Strong ultraviolet radiation from nearby stars can do this, dissociating hydrogen molecules and keeping the gas hot. In regions bathed in this radiation, gas clouds could grow to tens of thousands or even hundreds of thousands of solar masses before collapsing. The result would be a black hole much more massive than any star could produce, a supermassive seed ready to grow into a quasar. Direct collapse black holes and primordial black holes aren't mutually exclusive. Both could exist, contributing to the population of seed black holes in the early universe. Primordial black holes would form first, within the first second. Direct collapse black holes would form later, perhaps 100 million years after the Big Bang, when the first galaxies and stars were beginning to light up the cosmos. Together, they'd provide a range of seed masses, from hundreds to millions of solar masses, distributed throughout the young universe. Observational evidence for heavy seeds is circumstantial but mounting. The existence of billion solar mass black holes at high redshift is itself a strong hint. Theoretical models that start with stellar mass seeds struggle to explain these objects without invoking continuous super-Eddington accretion or mergers with other black holes at unrealistic rates. Models that start with intermediate mass seeds have an easier time. The growth curves fit the observations more naturally without requiring extreme fine-tuning. Gravitational wave detections add another layer. LIGO and Virgo have observed mergers involving black holes in the upper mass gap, the range where stellar black holes shouldn't exist due to pair instability supernovae. These objects could be primordial, formed with masses in this forbidden range. Alternatively, they could be the products of hierarchical mergers, smaller black holes merging repeatedly until they reach masses too high for stellar origins. Either way, they suggest a population of black holes with formation pathways different from standard stellar evolution. The distribution of supermassive black holes across cosmic time also provides clues. If all supermassive black holes grew from stellar seeds, their abundance should increase gradually over time, as more stars die and more seeds become available. Instead, quasars peak in abundance around 2 to 3 billion years after the Big Bang, then decline. This rise and fall suggests that seed black holes were plentiful early on, perhaps seeded by primordial black holes or direct collapse events, and that the later decline reflects exhaustion of gas supplies rather than a lack of seeds. There's also the question of black hole spins. When black holes grow by accreting gas from a disk, the disk's angular momentum gets transferred to the black hole, spinning it up to near maximal rotation. When black holes grow by merging with other black holes, the spin depends on the orientations and orbits of the merging objects. Measurements of supermassive black hole spins, inferred from the shapes of X-ray emission lines, show a wide range. Some are spinning rapidly, others slowly. This diversity could reflect mixed formation histories. Some black holes grew mainly by accretion, others mainly by mergers. If primordial black holes seeded the population, their initial spins would be random, adding another source of diversity. The spatial distribution of early quasars is also telling. They're found in regions that would later become massive galaxy clusters, areas where the density of matter was slightly higher than average. This makes sense if the seeds of supermassive black holes were themselves products of overdense regions, either primordial black holes that formed in the densest parts of the early universe, or direct collapse black holes that formed in the first protogalaxies. The correlation between early quasars and later large-scale structure hints at a deep connection between the initial conditions set by inflation and the eventual formation of the most massive objects. Upcoming telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will probe even earlier epochs, searching for the first quasars and the seeds from which they grew. If primordial black holes or direct collapse black holes are common, these observations should reveal black holes more massive than expected at earlier times than expected. The James Webb Space Telescope has already begun finding surprisingly massive galaxies in the first few 100 million years after the Big Bang, suggesting that structure formation happened faster than standard models predict. Massive seed black holes could be part of the explanation. There's also the possibility of detecting intermediate mass black holes directly, not as seeds, but as free-floating objects that never grew into supermassive giants. These orphan black holes, ranging from hundreds to hundreds of thousands of solar masses, would drift through galaxies or lurk in the outskirts. They're difficult to detect because they don't accrete much material and don't shine brightly. But gravitational waves from their mergers or microlensing of background stars could reveal their presence. Finding a population of intermediate mass black holes would strengthen the case for heavy seeds, whether primordial or formed by direct collapse. The connection between primordial black holes and supermassive black holes closes a loop in cosmic history. The conditions that created primordial black holes in the first second, inflation, quantum fluctuations, gravitational collapse, are the same conditions that set the stage for everything that followed. The seeds planted in that first moment grew into the monsters at the hearts of galaxies, shaping the evolution of cosmic structure. If primordial black holes really did seed supermassive black holes, it means the earliest instant of the universe left a legacy that persists today, billions of years later, in every quasar, every active galaxy, every black hole that devours matter and emits jets visible across cosmic distances. The cosmic dawn, that murky period when the first stars ignited and the first galaxies assembled, is still poorly understood. We see its afterglow in the cosmic microwave background and its mature products in distant galaxies, but the transition itself remains veiled. Primordial black holes offer a thread connecting the Big Bang to the first quasars, a narrative that spans from quantum fluctuations to billion solar mass monsters. Following that thread might reveal not just how supermassive black holes formed, but how the universe transitioned from simplicity to complexity, from a smooth plasma to a cosmos filled with structure and light. The multiverse connection and eternal inflation. Inflation doesn't just solve problems about our universe, it creates an infinite number of universes, each with its own properties, histories, and laws of physics. This is the multiverse, a consequence of eternal inflation, and it's one of the strangest predictions of modern cosmology. If inflation is true, and if it operates the way most models suggest, then our universe is just one bubble in an endlessly inflating cosmos, a single island in an infinite sea. Primordial black holes connect to this grand picture in unexpected ways, serving as both relics of our universe's birth and potential windows into the structure of the multiverse itself. Eternal inflation arises from the quantum nature of the inflaton field. In most regions of space, inflation ends when the inflaton rolls to the minimum of its potential, converting its energy into particles and radiation. But quantum fluctuations can push the field back up the potential in some regions, restarting inflation locally. Those regions expand exponentially, spawning new regions where inflation continues. The process never truly ends globally. It's eternal. New inflating regions constantly bud off, each eventually transitioning into a post-inflationary universe like ours. Each bubble universe in the eternally inflating multiverse could have different properties. The fundamental constants, the strength of gravity, the mass of the electron, the cosmological constant, might vary from bubble to bubble, determined by how the inflaton field and other fields settled into their vacuum states. Some bubbles would be stillborn, unable to form atoms or stars. Others would be profligate, producing galaxies and complexity far beyond what we see. Our universe sits somewhere in the middle, with constants finely tuned for structure formation and life. Primordial black holes in this picture become fossils of the multiverse's structure. If our bubble universe formed in a region where inflation was particularly violent, with large density fluctuations, primordial black holes would be abundant. If we formed in a calmer region, they'd be rare. The abundance and mass distribution of primordial black holes encode information about where we sit in the landscape of possibilities, a fingerprint of our cosmic origins. There's also the possibility that primordial black holes could form at the boundaries between bubble universes. When two bubbles collide, an event that might happen in the eternally inflating multiverse, the collision could create shock waves in space-time, regions of extreme density that collapse into black holes. These collision-born black holes would have unique properties, potentially distinguishable from those formed by standard density fluctuations. Their masses might cluster at specific values determined by the energy scales of the colliding bubbles. Detecting evidence of a bubble collision in our universe is one of the holy grails of multiverse cosmology. Such a collision would leave imprints in the cosmic microwave background, a circular pattern of temperature variations aligned in a specific direction. Searches for these patterns have found nothing conclusive, but the absence of evidence isn't evidence of absence. A collision could have occurred beyond our observable horizon, or the signal could be too faint to detect with current instruments. Primordial black holes from such a collision would be another signature, potentially more robust than the CMB imprint. The Anthropic principle enters the picture here. If the multiverse is real and contains an infinite variety of universes, most will be inhospitable to life. Only a tiny fraction will have the right conditions for complexity to emerge. In those rare universes, observers will inevitably find themselves simply because those are the only places where observers can exist. This anthropic reasoning applies to primordial black holes too. If black holes are abundant enough to significantly affect structure formation or the habitability of galaxies, we'd expect to live in a universe where their abundance is just right. Not so many that they disrupt planet formation, not so few that they fail to seed galaxies. Critics of the multiverse argue that it's unfalsifiable, a theory that predicts everything and therefore predicts nothing. If any observation can be explained by saying, "We just happen to live in a universe where that's true," the theory loses explanatory power. Proponents counter that the multiverse is a prediction of inflation, not an ad hoc addition. If you accept inflation, eternal inflation follows naturally from the dynamics. And while individual bubble universes might be unobservable, the multiverse as a whole makes statistical predictions that could be tested with large enough datasets. Primordial black holes offer a potential test. If their abundance and properties match predictions from specific inflation models, it constrains which models are viable. If they show patterns consistent with eternal inflation, say, a distribution that looks like it was drawn from a landscape of possibilities, rather than a single finely tuned model, it would support the multiverse picture. Conversely, if primordial black holes are absent, or have properties inconsistent with inflation, it would challenge the framework. There's also the question of whether primordial black holes could survive the transition from inflation to the radiation-dominated era. In some models of eternal inflation, the transition is smooth, and structures like primordial black holes form seamlessly. In others, the transition is violent, with reheating processes that could disrupt or destroy black holes. Understanding the details of reheating, how the inflaton's energy converts into particles, how temperatures and densities evolve, is crucial for predicting whether primordial black holes persist. Another exotic possibility is that primordial black holes could contain information about the pre-inflationary universe. Before inflation began, the universe might have existed in a different state, a contracting phase, a quantum fluctuation, a parent universe undergoing its own evolution. Inflation erases most traces of this pre-inflationary era, smoothing away structures and amplifying quantum noise. But primordial black holes, if they formed from rare overdensities that predated inflation, might retain signatures of the earlier epoch. Analyzing their properties could, in principle, reveal clues about the state of the universe before inflation took over. The connection to string theory adds another layer. String theory predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws and constants. Eternal inflation populates this landscape, with different bubble universes settling into different vacua. Primordial black holes might form preferentially in certain regions of the landscape, where the energy scales and dynamics favor their creation. Mapping the distribution of primordial black holes could indirectly map the structure of the string landscape, identifying which vacua are realizable and which are purely theoretical. Primordial black holes could also play a role in the cosmological constant problem. The observed value of the cosmological constant, the energy density of empty space, is extraordinarily small compared to theoretical predictions, smaller by a factor of 10 to the 120. This enormous discrepancy is one of the biggest unsolved problems in physics. In the multiverse picture, the cosmological constant varies from bubble to bubble, and we find ourselves in a bubble where it's small enough to allow structure formation. Primordial black holes, by affecting how structure forms and evolves, might influence the range of cosmological constants compatible with observers. Understanding their role could refine anthropic arguments about why our universe has the constants it does. The idea of the multiverse is unsettling to many physicists. It suggests that most of the cosmos is forever beyond our reach, that we can never fully test the theory because we can only observe our own bubble. Yet it's a logical consequence of taking inflation seriously. If the inflaton field undergoes quantum fluctuations, and if those fluctuations can restart inflation locally, eternal inflation is inevitable. Primordial black holes don't prove the multiverse, but they're woven into its fabric, products of the same dynamics that generate endless bubble universes. If we ever confirm the existence of primordial black holes and measure their properties precisely, we'll be learning not just about our own universe, but about the multiverse that birthed it. We'll see the fingerprints of eternal inflation, the echoes of quantum fluctuations blown up to cosmic scales, the remnants of a process that's still happening somewhere beyond our horizon. In that sense, primordial black holes are more than astronomical objects. They're messages from the deepest structure of reality, hints of the unimaginable vastness that lies beyond the observable universe. When black holes collide with neutron stars, black holes aren't the only compact objects born from stellar death. Neutron stars, the crushed cores of massive stars that didn't quite make it to black hole status, pack roughly 1.5 times the Sun's mass into a sphere only 20 kilometers across. They're made almost entirely of neutrons, crushed together at densities that make atomic nuclei look like empty space. When a black hole and a neutron star collide, the result is one of the most violent events in the universe, and the signatures of such mergers could help distinguish primordial black holes from their stellar cousins. The first confirmed detection of a black hole neutron star merger came in 2019, when LIGO and Virgo detected gravitational waves from an event labeled GW190814. The system involved a black hole of about 23 solar masses and a companion object of around 2.5 solar masses. That companion sits right on the boundary between the heaviest possible neutron stars and the lightest known black holes, a region called the mass gap. Whether it was a heavy neutron star or a light black hole is still debated, but the event opened a new window on compact object mergers. Black hole neutron star mergers differ from black hole mergers in crucial ways. When two black holes merge, they spiral together and coalesce, releasing gravitational waves but no light. The event is purely gravitational, invisible to traditional telescopes. But when a black hole tears apart a neutron star, the neutron star's material gets shredded and ejected, forming a debris disk around the merged object. This disk glows across the electromagnetic spectrum, from gamma rays to radio waves, creating a Kilanova, a transient burst of light powered by radioactive decay of heavy elements synthesized in the ejecta. Kilanovae are important because they produce heavy elements like gold, platinum, and uranium. These elements can't form in normal stellar fusion. They require the extreme conditions of neutron-rich environments. When a neutron star is torn apart, its material, loaded with neutrons, undergoes rapid neutron capture, building up heavy nuclei in a process called the R process. The ejecta from a single black hole neutron star merger could produce several Earth masses of gold. Over cosmic history, these mergers are thought to be a primary source of heavy elements in the universe. For primordial black holes, black hole neutron star mergers offer a diagnostic. If primordial black holes are common and distributed throughout the galaxy, they'd occasionally encounter neutron stars, which form continuously as massive stars die. The merger rate would depend on the local density of both populations. If primordial black holes dominate the dark matter, they'd be everywhere, and the merger rate with neutron stars would be high. Detecting an unexpectedly large number of black hole neutron star mergers could indicate a population of primordial black holes lurking in galactic halos. The mass of the black hole in such a merger also provides clues. Stellar mass black holes typically range from about 5 to 50 solar masses, with a clustering around 10 to 20 due to the details of stellar evolution. Primordial black holes, on the other hand, could have a different mass distribution, potentially with peaks at unusual values. If LIGO detects black hole neutron star mergers where the black hole has a mass that doesn't fit stellar models, say 2 solar masses or 100 solar masses, it would hint at a primordial origin. The dynamics of the merger depend on the mass ratio and the black hole's spin. If the black hole is much heavier than the neutron star gets swallowed whole before it can be torn apart. The merger produces gravitational waves, but no electromagnetic signal. No kilonova, no gamma-ray burst. If the black hole and neutron star are closer in mass, or if the black hole is spinning rapidly, tidal forces can shred the neutron star before it crosses the event horizon. The resulting debris creates a bright, detectable kilonova. By measuring whether electromagnetic counterparts accompany gravitational wave detections, astronomers can constrain the mass ratios and spins of the merging objects. Primordial black holes might have different spin distributions than stellar black holes. Stellar black holes inherit angular momentum from the collapsing core of their progenitor star, typically resulting in high spins. Primordial black holes, forming from overdensities in the early universe, would have random, low spins on average. A population of low-spin black holes merging with neutron stars would produce different tidal effects, potentially leaving distinctive signatures in the gravitational waveforms. The locations of black hole neutron star mergers also matter. Stellar black holes and neutron stars form in galaxies, particularly in star-forming regions. Primordial black holes would be distributed more broadly following the dark matter halo. If mergers are detected in the outskirts of galaxies or in intergalactic space, far from where stars form, it would suggest primordial black holes. Localizing the sources precisely is challenging, but multi-messenger observations, combining gravitational waves with electromagnetic signals, improve localization dramatically. Another factor is the chemical composition of the Kilanova ejecta. Neutron star material is extreme. Densities beyond anything achievable in laboratories, matter in states that push the limits of nuclear physics. When this material is ejected, its composition reflects the conditions inside the neutron star. By analyzing the spectrum of kilonova light, astronomers can infer the properties of the neutron star and, indirectly, the dynamics of the merger. If the black hole involved was primordial, with a mass or spin different from stellar expectations, the kilonova spectrum might show subtle anomalies. There's also the question of how often these mergers happen. Stellar black holes and neutron stars form in binary systems where two massive stars orbit each other. When one star dies, it becomes a compact object. When the other dies, it becomes another compact object. The two spiral together over millions to billions of years, eventually merging. The rate of these mergers depends on the frequency of massive binaries, the kick velocities imparted during supernova explosions, and the efficiency of orbital decay. Primordial black holes don't face these constraints. They formed independently, and their merger rate is determined purely by gravitational dynamics and the local density. If primordial black holes make up a significant fraction of dark matter, their encounters with neutron stars would create a steady background of mergers, detectable by current and future gravitational wave observatories. The rate would scale with the density of primordial black holes in the galaxy, higher in the inner regions, lower in the outskirts. Mapping the spatial distribution of merger events could reveal whether primordial black holes follow the dark matter halo or the distribution of stars and gas. LIGO Virgo and the upcoming KGRA and LIGO India detectors will build a more complete picture of compact object mergers. Each new detection adds to the catalogue, refining our understanding of the masses, spins, and rates. If a pattern emerges, mergers with unusual mass ratios, unexpected locations, or missing electromagnetic counterparts, it could point to primordial black holes. The challenge is distinguishing these signals from the noise of astrophysical variability, where every star and every galaxy has its own history. Black hole neutron star mergers also test our understanding of extreme matter. Neutron stars are the densest stable objects in the universe, and their internal structure is still uncertain. At the core, densities might exceed that of atomic nuclei, entering regimes where quarks and gluons become deconfined. The equation of state, the relationship between pressure and density, determines how large a neutron star can be before it collapses into a black hole. By observing how neutron stars behave during mergers, we constrain the equation of state, narrowing the range of possibilities. If primordial black holes frequently merge with neutron stars, the population of neutron stars in the galaxy would gradually decline, consumed by black holes over billions of years. This effect would be subtle, difficult to detect directly, but it might show up in the statistics of neutron star populations. If certain regions of the galaxy have fewer neutron stars than expected, or if old neutron stars are rarer than they should be, it could hint at a hidden population of primordial black holes steadily devouring them. The mergers between black holes and neutron stars are cosmic laboratories where gravity, nuclear physics, and the dynamics of extreme matter converge. Each detection is a snapshot of the universe at its most violent. A fleeting moment when space-time warps, elements are forged, and light flashes across billions of light years. For primordial black holes, these mergers are both a challenge and an opportunity. A challenge because they must fit into the complex ecosystem of compact objects. And an opportunity because they offer unique signatures that could finally prove these ancient relics exist. Hawking radiation and the death of small black holes. Stephen Hawking's realization in 1974 that black holes aren't entirely black transformed our understanding of these objects. Before Hawking, black holes were seen as perfect traps, regions of space-time where matter and energy could enter but never leave. Hawking showed that quantum effects near the event horizon cause black holes to emit radiation, slowly evaporating over time. For large black holes, the effect is negligible. For small primordial black holes, it's everything. The mechanism behind Hawking radiation involves virtual particles, fleeting quantum fluctuations that constantly pop into and out of existence throughout space. Normally, these particle-antiparticle pairs annihilate almost instantly, contributing nothing observable. But near a black hole's event horizon, the intense gravitational field can separate the pair before they annihilate. One particle falls into the black hole, while the other escapes to infinity. To an outside observer, it looks like the black hole is emitting particles. The energy for this radiation comes from the black hole's mass. Each emitted particle carries away energy, and by Einstein's mass-energy equivalence, the black hole shrinks. The process is excruciatingly slow for large black holes. A solar mass black hole radiates at a temperature of about 60 nanokelvins. far colder than the cosmic microwave background. It would take 10 to the 67 years for such a black hole to evaporate completely, vastly longer than the current age of the universe. But for small black holes, the story is different. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A black hole with the mass of a mountain radiates at temperatures of billions of Kelvin, glowing white hot. It loses mass rapidly, evaporating in less than the current age of the universe. Any primordial black hole lighter than about 10 to the 15th grams would have already evaporated by now, exploding in a final burst of gamma rays and elementary particles. This sets a lower mass limit on surviving primordial black holes. Anything lighter is gone. The final moments of a black hole's life are spectacular. As it shrinks, it radiates hotter and faster, accelerating toward a runaway explosion. In the last second of its life, a black hole might release energy equivalent to millions of nuclear bombs, a cosmic firework visible across vast distances. No one has ever observed such an event, but the predictions are clear enough that astronomers have searched for the gamma-ray signatures. Space-based observatories like Fermi and Integral scan the sky continuously, recording transient bursts. None have been definitively linked to evaporating black holes. The absence of detected explosions constrains the population of light primordial black holes. If they formed in large numbers during the Big Bang, we'd see their death throes scattered across the sky. The fact that we don't means either they're rare or they never formed at all in the mass ranges where evaporation is relevant. This tightens the allowed parameter space for primordial black hole formation models. Whatever process created them couldn't have produced too many light ones. Hawking radiation also creates theoretical puzzles. When a black hole evaporates, what happens to the information about the matter that fell in? In quantum mechanics, information is conserved. It can't be destroyed. But Hawking radiation is thermal, carrying no information about what went into the black hole. If the black hole evaporates completely, the information seems to vanish, violating a fundamental principle of quantum mechanics. This is the black hole information paradox, and it's one of the deepest problems in theoretical physics. Proposed solutions involve modifications to how we think about black holes and quantum gravity. Some suggest that information escapes gradually through subtle correlations in the Hawking radiation, too small to detect with current technology, but present nonetheless. Others propose that black holes don't evaporate completely, leaving behind a remnant, a Planck mass object that contains all the information in a compressed form. Still others argue that the event horizon isn't a sharp boundary, but a fuzzy region, where quantum effects blur the distinction between inside and outside. Primordial black holes offer a unique test case for these ideas. Unlike stellar black holes, which form from collapsing stars and have well-defined formation histories, primordial black holes emerge directly from the quantum foam of the early universe. If information is encoded in the initial conditions, the precise configuration of the density fluctuation that collapsed, then tracking that information through the black hole's lifetime and eventual evaporation might reveal how quantum gravity resolves the paradox. Detecting Hawking radiation directly would be a monumental achievement, confirming a cornerstone prediction of quantum field theory in curved spacetime. But the signal is weak. Even for a black hole radiating at billions of Kelvin, the flux at Earth would be tiny unless the black hole was very close. Searches focus on gamma-ray bursts with specific spectral properties, looking for events that match the predicted signatures of evaporating primordial black holes. So far, the searches have come up empty, but each non-detection refines the constraints. There's also the possibility of detecting Hawking radiation indirectly through its effects on the surrounding environment. A primordial black hole radiating in a dense gas cloud would heat the gas, creating a bubble of hot ionized material. This bubble might be detectable through X-rays or radio emissions. In the early universe, before the first stars formed, such bubbles could have ionized the intergalactic medium, leaving imprints on the cosmic microwave background. Searches for these imprints constrain the abundance of radiating primordial black holes in the early universe. Hawking radiation becomes even stranger when you consider the final stages. As a black hole shrinks toward the Planck mass, about 10 to the negative 5 grams, quantum gravity effects become dominant. General relativity breaks down, and the smooth space-time picture dissolves into something more fundamental, perhaps a network of quantum loops or vibrating strings. What happens in those final moments is unknown. Does the black hole disappear entirely? Does it leave a remnant? Does it tunnel into another state, perhaps creating a baby universe? These questions push the boundaries of known physics, venturing into territory where theory is speculative and experiments are impossible. For primordial black holes just above the evaporation threshold, masses around 10 to the 15th grams, the situation is critical. They're stable over the age of the universe, but they're radiating noticeably. Over billions of years, they lose a measurable fraction of their mass. If dark matter includes a population of these black holes, they'd be slowly converting from mass into radiation, gradually reducing their contribution to the total dark matter budget. This makes them a less stable form of dark matter than particles, which don't decay. The spectrum of Hawking radiation also carries information. It's not purely thermal, there are subtle deviations that encode details about the black hole's spin, charge, and quantum state. For primordial black holes, which might have unusual properties due to their formation mechanism, these deviations could provide signatures distinguishing them from other objects. Analyzing the spectrum of a detected gamma-ray burst and comparing it to Hawking radiation predictions could reveal whether the source was an evaporating black hole, and, if so, what kind. Hawking radiation connects black holes to thermodynamics in profound ways. A black hole has entropy proportional to the area of its event horizon, not its volume, a result that hints at the holographic principle, the idea that information in a volume of space can be encoded on its boundary. When a black hole radiates, its entropy decreases, but the entropy of the emitted radiation increases. The second law of thermodynamics holds, but barely. Understanding this balance requires a quantum theory of gravity, something we don't yet have. Primordial black holes evaporating through Hawking radiation are windows into quantum gravity, the ultimate theory that unites general relativity and quantum mechanics. They're natural laboratories operating at energy scales far beyond what particle accelerators can reach. If we could observe one evaporating, measure its radiation spectrum, and track the information flow, we'd learn more about the fundamental structure of space-time than from almost any other observation. The fact that we haven't seen one yet doesn't mean they don't exist. It might just mean we haven't looked hard enough, or in the right places, or with the right tools. The evidence that undercuts primordial black holes. Despite the tantalizing hints and the elegant solutions they offer, primordial black holes face serious challenges. Many physicists remain skeptical, pointing to constraints from observations, difficulties with formation mechanisms, and the lack of direct detections. The case against primordial black holes is strong enough that they remain controversial, a hypothesis rather than an established fact. Understanding the skeptics' arguments is essential for evaluating whether these objects are real or a theoretical mirage. The most straightforward objection is observational. If primordial black holes make up a significant fraction of dark matter, they should have left detectable traces. Gravitational microlensing surveys, monitoring millions of stars for decades, have found fewer events than expected if primordial black holes dominated the dark matter. The Macho and Eros projects in the 1990s and 2000s ruled out primordial black holes in certain mass ranges, particularly around one solar mass. Follow-up surveys have extended these constraints, narrowing the windows where primordial black holes can hide. Constraints from the cosmic microwave background are particularly tight. If primordial black holes were abundant during the era of recombination, they'd accrete gas, injecting energy into the surrounding plasma. This would alter the ionization history of the universe, changing the statistical properties of the microwave background in ways we don't observe. The precision of Planck satellite measurements leaves little room for large populations of primordial black holes heavier than 10 solar masses. Either they're rare, or their accretion was suppressed in ways that seem contrived. Wide binary stars provide another constraint. These fragile systems, with components separated by thousands of astronomical units, survive in the Milky Way despite being vulnerable to gravitational disruption. If primordial black holes were common, passing through the galaxy over billions of years, they'd tear apart many wide binaries. The fact that so many wide binaries remain intact suggests that primordial black holes heavier than a few tens of solar masses can't dominate the local dark matter. The constraint isn't absolute. It depends on assumptions about how primordial black holes move through the galaxy, but it's difficult to evade. Dynamical heating in globular clusters provides similar limits. These ancient stellar systems are dense and tightly bound. If massive compact objects like primordial black holes pass through them frequently, the gravitational interactions would pump energy into the system, causing it to expand. Observations show that globular clusters remain compact, which constrains the flux of primordial black holes through these regions. Again, the constraint can be weakened by adjusting assumptions, but it requires the primordial black holes to have specific velocity distributions or spatial clustering that aren't naturally predicted. The formation mechanisms themselves face challenges. In standard inflation models, the density fluctuations are too small and too uniform to produce significant numbers of primordial black holes. The power spectrum is nearly scale invariant, with fluctuations of about 1 part in 100,000 at all scales. For primordial black holes to form, you need fluctuations of order 1, thousands of times larger than typical. Achieving this requires special features in the inflaton potential, bumps, plateaus, or periods of ultra-slow roll that amplify fluctuations at specific scales. These features aren't predicted by the simplest inflation models. They're added by hand to make primordial black hole formation possible. Critics argue this is fine-tuning, adjusting the theory to fit a desired outcome rather than making genuine predictions. Proponents counter that simple inflation models are just that, simple. There's no reason the inflaton potential has to be a smooth, quadratic curve. Physics at the energy scales of inflation is poorly understood, and complex potentials with features are perfectly plausible. The debate hinges on philosophy as much as physics. Do we prefer simpler models with fewer free parameters, or more complex models that explain more phenomena? The absence of detected Hawking radiation from evaporating primordial black holes is another point against them. If black holes lighter than about 10 to the 15th grams formed in the early universe, they should be exploding now, emitting detectable gamma-ray bursts. Space-based observatories have searched for these signatures for decades without success. This doesn't rule out heavier primordial black holes, which evaporate too slowly to have finished yet, but it does constrain the abundance of light ones. Either they're extremely rare, or they never formed in significant numbers. Gravitational wave detections, while tantalizing, aren't definitive. The black hole mergers LIGO has observed could all be explained by stellar evolution in low metallicity environments, where stars lose less mass and produce heavier black holes. The merger rates, while higher than some early predictions, aren't so high that they demand a primordial population. The mass distributions, while broader than expected, overlap with what stellar models allow. Every anomaly that hints at primordial black holes can also be explained with some effort by adjusting parameters in stellar evolution models. The spins of black holes detected by LIGO provide another test. Stellar black holes should have spins correlated with the binary orbit, while primordial black holes should have random spins. Early results suggested some mergers had misaligned or low spins, consistent with primordial origins, but as more events have been detected, the picture has become muddier. Many mergers show high spins and aligned orientations, exactly what you'd expect from stellar binaries. The diversity might just reflect the variety of formation channels for stellar black holes, not a primordial population. Microlensing events toward the Magellanic Clouds, once cited as potential evidence for primordial black holes, have alternative explanations. Most can be attributed to ordinary stars, brown dwarfs, or white dwarfs in the galactic halo. The excess events that initially seemed unexplained might be statistical flukes, or they might arise from a population of stellar remnants we hadn't fully accounted for. Distinguishing between these possibilities requires more data and better modeling of the galactic halo's composition. The direct collapse mechanism for forming massive seed black holes, while plausible, isn't guaranteed to work. Simulations show that under the right conditions, strong UV radiation to suppress molecular hydrogen cooling, rapid gas inflows to prevent fragmentation, a gas cloud can collapse directly into a massive black hole. But the right conditions are specific and might be rare. Many simulations show that instead of collapsing monolithically, the gas fragments into clumps that form stars first. Only a subset of scenarios lead to direct collapse, and it's unclear how common those scenarios were in the early universe. Primordial black holes also create problems if they're too abundant. If they dominated the dark matter, they'd overseed structure formation, creating more massive galaxies earlier than we observe. They'd disrupt molecular clouds, preventing star formation in regions where we see stars forming. They'd produce too many microlensing events, too many dynamical interactions, too many accretion signatures. To avoid these problems, primordial black holes must be fine-tuned in their abundance and distribution, occupying a narrow sweet spot where they're common enough to matter, but not so common they cause trouble. The information paradox, while fascinating, isn't resolved by primordial black holes. Whether a black hole formed from a collapsing star or from a density fluctuation in the early universe, it still faces the same quantum conundrum when it evaporates. Primordial black holes don't make the paradox easier to solve, they just provide more examples of it. If anything, they make it more urgent, because some primordial black holes might be evaporating right now, destroying information in real time. But urgency isn't the same as insight. There's also the issue of dark matter's observed properties. Dark matter behaves like cold, collisionless particles, clustering on galactic scales but not on smaller ones. Primordial black holes, being point masses, cluster more strongly than particles, forming dense cores and exhibiting different dynamics. Simulations of galaxy formation with primordial black holes as dark matter show subtle differences from particle dark matter simulations. These differences might already be ruled out by observations of galactic rotation curves, dwarf galaxy distributions, or the Lyman alpha forest, wiggles in the spectra of distant quasars caused by intervening gas clouds. Critics also point out that invoking primordial black holes doesn't really solve the dark matter problem. It just replaces one mystery with another. Instead of asking, what is dark matter made of? We're asking, how did density fluctuations get large enough to form primordial black holes? The latter question pushes the mystery back to inflation, to the early universe, to physics we don't fully understand. It's not clear this is progress. We've traded an unknown particle for an unknown mechanism, and in the process, we've added complexity to inflation models that were already under-constrained. Some physicists argue that the continued failure to detect particle dark matter should make us more open to alternatives like primordial black holes. Others argue the opposite. The absence of particle detections after decades of searching doesn't invalidate the particle hypothesis. It just means we haven't searched the right parameter space yet. Dark matter could be axions at masses we haven't probed, sterile neutrinos with properties we haven't tested, or some other particle that's simply more elusive than WIMPs. Giving up on particles to embrace primordial black holes might be premature, swapping one speculative idea for another. There's also aesthetic resistance. Primordial black holes feel ad hoc to some physicists. They require special conditions during inflation, fine-tuned abundances to avoid observational constraints, and complex formation mechanisms that aren't naturally predicted. Particle dark matter, despite decades of null results, emerges naturally from many theories beyond the standard model. Supersymmetry, for instance, automatically predicts stable massive particles that could be dark matter. String theory compactifications often produce axion-like particles. These aren't retrofitted explanations. They're predictions that came before the dark matter problem was fully appreciated. The skeptic's strongest card is simply the lack of a smoking gun. After years of searching, we have no unambiguous detection of a primordial black hole. Every hint, unusual gravitational wave signals, microlensing anomalies, fast-growing supermassive black holes, can be explained by conventional astrophysics with some adjustment of parameters. Until we find something that absolutely requires primordial black holes, something that cannot be explained any other way, they remain a hypothesis. Interesting, well-motivated, but unproven. Yet science advances through exactly this kind of debate. Hypotheses are proposed, tested against observations, refined or discarded based on evidence. Primordial black holes have survived longer than many speculative ideas because they keep finding new life in unexpected places. Every time constraints seem to rule them out in one mass range, theorists find another range where they could hide. Every time one formation mechanism is challenged, another emerges. This resilience could mean primordial black holes are real and we're gradually narrowing in on them. Or it could mean the idea is too flexible, able to accommodate any observation by adjusting parameters, and therefore unfalsifiable. Time and better data will tell. Detecting the undetectable through gravitational lensing. If primordial black holes pervade the universe as dark matter, they're constantly passing between us and distant light sources, warping spacetime and bending light. This gravitational lensing effect is one of the most promising ways to detect them. Unlike searching for accretion signatures or gravitational waves from mergers, lensing works even if primordial black holes are completely isolated, drifting through the cosmos without interacting with anything. Every photon that passes near a primordial black hole carries information about its presence, encoded in subtle shifts of position and brightness. The principle is straightforward. Light travels in straight lines through flat space-time, but space-time near a massive object is curved. Photons follow the curvature, bending their paths around the mass. When a primordial black hole passes between Earth and a distant star, it acts as a gravitational lens, temporarily magnifying the star's light. The star brightens, then fades back to normal as the black hole moves on. The duration and shape of this brightening depend on the black hole's mass, distance, and velocity. By measuring these properties, astronomers can infer the lens's characteristics. For stellar mass primordial black holes, lensing events last weeks to months. A 30 solar mass black hole passing in front of a star in the Magellanic Clouds would cause the star to brighten by factors of 2 to 10 over a period of roughly 50 days. The light curve, the graph of brightness versus time, follows a characteristic shape, a smooth rise, a peak, and a symmetric fall. This shape distinguishes gravitational lensing from other causes of stellar variability, like pulsations or eclipses, which have different patterns. Microlensing surveys have been monitoring millions of stars for decades, searching for these events. The OGLE project, based in Poland, watches stars in the Magellanic Clouds and the galactic bulge. The MOA project in New Zealand focuses on similar targets. Between them, they've detected thousands of microlensing events, most caused by ordinary stars or brown dwarfs in the Milky Way's halo. But mixed in with these could be events caused by primordial black holes. The challenge is distinguishing the two, a lensing event caused by a star and one caused by a black hole of the same mass produce nearly identical light curves. The only difference is the nature of the lens, and that's invisible. Astronomers can measure the mass of the lens indirectly through the duration and amplitude of the event, but mass alone doesn't tell you whether the lens is a star or a black hole. You need additional information, color, brightness, proper motion, to rule out stellar lenses. If the lens is too massive to be a star and shows no electromagnetic emission, it's a candidate for a primordial black hole. Some surveys have tried this approach, looking for lensing events where the inferred mass is high, but no stellar counterpart is detected. The results have been ambiguous. A few events fit the profile, but not enough to establish a population. Either primordial black holes are rare, or they're distributed in ways that make lensing events unlikely, or the surveys haven't reached sufficient sensitivity yet. Ongoing projects like the Vera Rubin Observatory, with its wide-field survey capabilities, will dramatically increase the sample size, improving the chances of detection. Gravitational lensing also works for lighter primordial black holes. An asteroid mass black hole, around 10 to the 15th grams, would lens a star for only a few hours. A lunar mass black hole would cause a lensing event lasting days. These shorter events are harder to catch because they require monitoring stars more frequently, but they're not impossible. High-cadence surveys, imaging the same fields every few minutes or hours, can detect rapid microlensing from light primordial black holes. The Kepler and TESS missions, designed to find exoplanets by watching for transits, have data that could be mined for these signals. Wave effects become important for very light primordial black holes. When the lens is small enough, comparable to the wavelength of light, diffraction and interference create complex patterns in the lensed light. Instead of a simple brightening, the star's light might flicker or show spectral distortions. These wave optics effects are difficult to predict precisely, but they provide a unique signature that distinguishes light primordial black holes from other lenses. Observing such an event would be strong evidence for a primordial black hole below a certain mass threshold. Lensing of gravitational waves offers another detection method. When a gravitational wave from a distant black hole merger passes near a massive object, like a primordial black hole, the wave is lensed just like light. The signal gets magnified, distorted, or split into multiple images, arriving at slightly different times. LIGO and Virgo can detect these effects, searching for patterns in their data that indicate lensing. So far, no confirmed lensed gravitational wave events have been found, but the search is in its early stages. As detectors improve and the catalogue of events grows, lensed signals should become detectable. Strong lensing by primordial black holes could create dramatic effects. If a primordial black hole passed directly in front of a quasar or galaxy, it would create multiple images of the background object arranged in a ring, an Einstein ring. For stellar mass primordial black holes, these rings would be tiny, far too small to resolve with current telescopes. But for intermediate mass or massive primordial black holes, thousands to millions of solar masses, the rings could be resolvable. Finding such an object, a perfect ring around an otherwise empty point in space, would be unmistakable evidence of a black hole with no visible accretion. Primordial black holes could also lens the cosmic microwave background. Photons from the CMB, traveling for nearly 14 billion years, pass through the large-scale structure of the universe on their way to us. Massive objects along the path lens these photons, distorting the temperature patterns we observe. If primordial black holes are abundant, they'd contribute to this lensing signal in distinctive ways. The statistical properties of CMB lensing depend on the distribution of mass in the universe, and primordial black holes would add fluctuations at specific scales corresponding to their masses. Analyzing CMB lensing requires sophisticated statistical techniques. The Planck satellite has produced detailed maps of the lensing potential, showing how mass between us and the CMB distorts the primordial temperature fluctuations. These maps agree with predictions from standard dark matter models, but there's room for contributions from primordial black holes. If they cluster in ways different from particle dark matter, the lensing signature would deviate from expectations, providing a subtle but detectable signal. Femtolensing pushes the technique to extreme scales. If ultralight primordial black holes exist, masses below an asteroid, they could lens gamma-ray bursts. Gamma-ray bursts are among the brightest events in the universe, visible across cosmic distances. If a tiny primordial black hole passed in front of a burst, it would modulate the gamma-ray flux on microsecond timescales, creating a flickering pattern characteristic of lensing. Detecting such an event requires instruments with extremely high time resolution and sensitivity, but it's within reach of current technology. The Fermi Gamma-Ray Space Telescope has data that could be searched for femtolensing signatures. Gravitational lensing has the advantage of being sensitive to all masses of primordial black holes, from the lightest that haven't evaporated to the heaviest that rival galaxies. Each mass range produces lensing events with characteristic durations and amplitudes, creating a spectrum of signals. By surveying the sky at different cadences and wavelengths, astronomers can probe the entire mass range, building a complete picture of the primordial black hole population, or confirming its absence. The next generation of surveys will be transformative. The Vera Rubin Observatory will image the entire southern sky every few nights, monitoring billions of stars and galaxies for transient events. The Nancy Grace Roman Space Telescope will conduct microlensing surveys toward the galactic bulge with unprecedented sensitivity. The Square Kilometre Array will monitor pulsars and radio transients, detecting lensing through timing variations. Together, these facilities will either find primordial black holes or constrain their abundance so tightly that only the narrowest windows remain. Gravitational lensing is the net cast wide enough to catch even the most elusive prey. The role in reionization and the first stars. The universe spent its first few 100 million years in darkness. After the cosmic microwave background was released and the universe became transparent, there were no stars yet, no galaxies, no sources of light beyond the fading afterglow of the Big Bang. This period, called the Cosmic Dark Ages, lasted until the first stars ignited, flooding space with ultraviolet radiation and beginning the process of reionization, turning the neutral hydrogen gas that filled the universe back into ionized plasma. Reionization is one of the major phase transitions in cosmic history, and understanding when and how it happened is a central goal of observational cosmology. The cosmic microwave background shows us the universe at 380,000 years, when it was neutral. Observations of distant quasars show us the universe at about 1 billion years, when it was fully ionized. Somewhere in between, reionization occurred. The question is, what caused it? The standard answer is the first stars and galaxies, but primordial black holes could have played a role too. If primordial black holes existed during the Dark Ages, they would accrete gas from the surrounding medium. Even a small black hole, drifting through the primordial hydrogen, would pull in material, heating it through friction as it spiraled toward the event horizon. This heated gas would radiate X-rays and ultraviolet light, ionizing nearby hydrogen atoms. A population of primordial black holes scattered through the early universe could contribute significantly to reionization, potentially even dominating over stars if the black holes were abundant enough. The energy injection from accreting primordial black holes would differ from that of stars. Stars emit primarily ultraviolet light, with spectra shaped by their surface temperatures and compositions. Primordial black holes, accreting from diffuse gas, would emit harder X-rays capable of ionizing hydrogen more efficiently and penetrating farther through the intergalactic medium. The ionization signature would be different, potentially detectable in the statistics of the cosmic microwave background or in the absorption spectra of distant quasars. Observations of reionization are challenging because the signals are faint and the epochs are far away. The James Webb Space Telescope is designed to observe the first galaxies and stars, probing the era when reionization began. Early results show galaxies appearing earlier and more massive than expected, suggesting rapid structure formation. If primordial black holes seeded these early galaxies or contributed to reionization, it would help explain the unexpected observations. The black holes would provide gravitational anchors for gas to collapse around and energy sources to ionize their surroundings. The 21 centimeter line of neutral hydrogen offers a direct probe of reionization. Before reionization, The intergalactic medium was filled with neutral hydrogen emitting faint radio waves at a wavelength of 21 centimeters. As reionization progressed, bubbles of ionized gas grew around the first stars and black holes, eating into the neutral medium. The distribution and size of these bubbles encode information about the sources of ionization. Radio telescopes like LOFAR, HERA, and the upcoming Square Kilometre Array are attempting to map the 21 centimeter signal across cosmic time, tracing the progress of reionization. If primordial black holes contributed significantly to reionization, the 21 centimeter signal would show distinctive features. The ionized bubbles around accreting black holes would be smaller and more numerous than those around galaxies, creating a different statistical pattern. The temperature of the neutral hydrogen would be affected by X-ray heating from black holes, shifting the frequency and amplitude of the 21 centimeter line. Detecting these signatures requires extraordinary sensitivity and control of systematic errors, but if successful, it would provide direct evidence for primordial black holes in the early universe. Primordial black holes could also affect the formation of the first stars. In the standard picture, the first stars formed in small dark matter halos, regions where gravity pulled gas together until it collapsed and ignited nuclear fusion. These stars were massive, hundreds of times the Sun's mass, burning hot and dying young. But if primordial black holes were present, they'd alter this process. A black hole settling into a dark matter halo would heat the gas through accretion, potentially preventing it from cooling enough to form stars. Alternatively, the black hole's gravity could help concentrate the gas, accelerating star formation. The interplay between primordial black holes and the first stars is complex, depending on the masses and abundances of the black holes, the density and temperature of the gas, and the dynamics of the dark matter halos. Simulations are beginning to explore this parameter space, but uncertainties are large. Different assumptions about primordial black holes lead to wildly different predictions for the first stars. More massive or less massive, forming earlier or later, in greater or smaller numbers. Observations of the most distant galaxies, like those being obtained by JWST, will eventually constrain these models. One intriguing possibility is that primordial black holes could suppress the formation of low-mass stars. In the present-day universe, stars form across a wide range of masses, from tiny red dwarfs to massive blue giants. But in the early universe, conditions might have favored more massive stars. If primordial black holes heated the gas, raising the temperature threshold for collapse, only the most massive gas clouds could overcome the pressure and form stars. This would explain why the first stars seem to have been so massive, and why low-mass stars from the early universe are rare or absent. Primordial black holes might also seed the formation of globular clusters, dense collections of stars that orbit galaxies. These clusters are among the oldest structures in the universe, and their origins are poorly understood. If a primordial black hole sat at the center of a collapsing gas cloud, it could attract material gravitationally, forming a dense stellar system around itself. The black hole would remain at the center, undetected, but inferred from the dynamics of the stars orbiting it. Some globular clusters do show evidence of central massive objects, consistent with intermediate mass black holes, though the evidence is debated. The chemical composition of the first stars also provides clues. Stars produce heavy elements through nuclear fusion, enriching the gas from which later generations of stars form. The first stars, forming from primordial gas with almost no heavy elements, would have unique chemical signatures. If primordial black holes influenced when and where these stars formed, the pattern of chemical enrichment across the universe would reflect their distribution. Anomalies in the abundances of certain elements, or unexpected variations in metallicity across different regions, could hint at the role of primordial black holes in early structure formation. Reionization and the formation of the first stars represent a crucial transition in cosmic history. from the simple, homogeneous universe of the Dark Ages to the complex, structured universe we see today. Primordial black holes, if they existed, would have been active participants in this transition, not passive bystanders. Understanding their role requires combining observations across multiple wavelengths, radio, infrared, X-ray, and comparing with sophisticated simulations. The coming decade of observations, with JWST, the Square Kilometre Array, and other facilities, will either reveal primordial black holes as key players in the cosmic dawn, or rule them out as bit players, leaving the spotlight to stars and galaxies alone. The search in particle accelerators and laboratory experiments. Primordial black holes are cosmic objects born in the first moments after the Big Bang, but their detection might not require looking to the stars. If ultralight primordial black holes exist, masses far below anything astrophysical, they could pass through Earth constantly, invisible but detectable through subtle effects on matter and instrumentation. Laboratories around the world have begun searching for these signals, turning particle detectors and precision instruments into black hole observatories. The smallest primordial black holes that could still exist today have masses around 10 to the 15th grams, roughly the mass of a large mountain. Anything lighter would have evaporated by now through Hawking radiation. But even at this lower limit, a primordial black hole would be extraordinarily dense, with an event horizon smaller than an atomic nucleus. Such an object passing through the Earth would interact only through gravity, leaving no trace except for the tiny gravitational disturbances it creates along its path. One detection strategy involves seismometers. A primordial black hole transiting the Earth would create a gravitational wake, a ripple in the planet's density that propagates as a shock wave. This shock wave would be incredibly weak, but global networks of seismometers designed to detect earthquakes and nuclear tests are sensitive enough to potentially catch it. The challenge is distinguishing a black hole transit from the countless other seismic signals, natural earthquakes, ocean waves, human activity that saturate the data. Sophisticated algorithms are being developed to search for the unique signature of a black hole passage, a pulse that travels in a straight line through the planet at a specific velocity. Gravitational wave detectors offer another avenue. While LIGO and Virgo are designed to detect waves from cosmic events like black hole mergers, they're also sensitive to local gravitational disturbances. A primordial black hole passing near a detector would create a transient gravitational signal, a brief tug on the mirrors that measure space-time curvature. The signal would be different from astrophysical sources, shorter, with a characteristic frequency determined by the black hole's mass and velocity. Continuous monitoring of the detector's data, searching for these transients, could reveal primordial black holes passing through the solar system. Atomic clocks provide exquisite sensitivity to gravitational effects. These devices measure time by counting oscillations of atoms in precisely defined states, achieving accuracies of 1 part in 10 to the 18th. A primordial black hole passing nearby would create a time dilation effect, causing the clock to run slightly slower during the encounter. By comparing the readings of multiple atomic clocks distributed across the Earth, researchers can search for correlated timing anomalies that indicate a gravitational disturbance. The effect would be minuscule, nanoseconds at most, but within the reach of current technology. Particle accelerators, ironically, could detect primordial black holes, even though they can't create them. The Large Hadron Collider at CERN and other facilities operate with extraordinary precision, monitoring particle beams and collision products with elaborate detector systems. A primordial black hole passing through the accelerator would deflect particle beams slightly, creating unexplained anomalies in the collision data. The black hole's gravitational field would act like an invisible lens, bending the paths of particles in ways that don't match the known magnetic and electric fields. Searching for these anomalies requires sifting through petabytes of data, but machine learning algorithms are making it feasible. Precision gravimeters, instruments that measure the local gravitational field with extreme accuracy, could detect primordial black holes passing underground. These devices are used in geophysics to map subsurface structures, measure tidal effects, and monitor volcanic activity. But they're also sensitive enough to detect a transient gravitational anomaly from a passing black hole. A network of gravimeters, positioned at different locations, could triangulate the trajectory of a black hole, determining its mass and velocity from the timing and amplitude of the signals. Quantum sensors are pushing the boundaries of measurement even further. These devices use quantum entanglement and superposition to achieve sensitivities beyond what classical instruments can reach. Quantum gravimeters, quantum accelerometers, and quantum magnetometers are all being developed, and all could potentially detect primordial black holes. The quantum states these devices rely on are exquisitely sensitive to external perturbations, including gravitational fields. A primordial black hole passing through a quantum sensor would decohere the quantum state in a characteristic way, leaving a signature that distinguishes it from other sources of noise. There's also the possibility of detecting secondary effects. A primordial black hole passing through a material object, a mountain, a building, even a human body, would compress the material along its path, creating microscopic stress patterns. These stresses might be detectable in crystalline structures, where atomic arrangements are highly ordered. After a black hole passage, the crystal lattice would show defects or dislocations aligned along the trajectory. Searching for such patterns in ancient rocks or meteorites might reveal evidence of primordial black hole transits over geological timescales. The search in laboratories complements astronomical observations. While telescopes look outward for gravitational lensing, accretion signatures, and gravitational waves from mergers, laboratories look inward, monitoring the immediate environment for direct encounters. The two approaches probe different mass ranges and populations. Astronomical observations are most sensitive to heavier primordial black holes, masses comparable to or greater than the Sun. Laboratory searches target the lightest primordial black holes, those just above the evaporation threshold, which would be too small to detect through lensing or mergers, but frequent enough to occasionally pass through detectors. One challenge with laboratory searches is the extremely low event rate. Even if primordial black holes make up all of the dark matter, their number density is small because their individual masses are large. A primordial black hole with the mass of a mountain passing through a detector the size of LIGO happens, on average, once every few thousand years. Catching such an event requires continuous monitoring over decades, combined with robust algorithms to avoid false positives from instrumental glitches or environmental noise. Collaborations are forming to coordinate these searches. The Global Seismic Network, networks of atomic clocks used for satellite navigation and timekeeping, and data from particle accelerators are all being analyzed for signs of primordial black hole transits. Pooling data from multiple sources increases the chances of detection and allows for cross-validation. If an anomaly appears in seismic data, does it correlate with a timing glitch in atomic clocks? If a gravitational wave detector registers a transient, do nearby gravimeters show simultaneous disturbances? Correlated signals across independent instruments would be strong evidence for a real event. The search in laboratories also has a philosophical dimension. For most of human history, our interaction with the cosmos was passive. We observed the stars, but they didn't touch us directly. Primordial black holes, if they exist and if we detect them, would be different. They'd be cosmic objects passing through our laboratories, through our instruments, through the very matter we're made of. The boundary between observing the universe and being part of it would blur. We wouldn't just be detecting primordial black holes, we'd be experiencing them in a very real and tangible way. That prospect, however remote, is what drives the search forward. Future missions and the next generation of detectors. The current generation of telescopes gravitational wave detectors, and particle physics experiments has pushed the search for primordial black holes to new frontiers, but the next decade will bring even more powerful tools. Missions in development promise to probe primordial black holes with unprecedented sensitivity, covering mass ranges and signatures that are currently inaccessible. If primordial black holes exist, these future instruments will likely find them. If they don't, the absence will be so conspicuous that the hypothesis will finally be put to rest. The Vera Rubin Observatory, set to begin operations in Chile, will revolutionize time-domain astronomy. With its massive 8.4-meter mirror and 3.2 gigapixel camera, it will image the entire visible sky every few nights, creating a comprehensive record of transient and variable phenomena. For primordial black holes, this means detecting microlensing events across billions of stars, building statistics robust enough to distinguish primordial populations from stellar lenses. The survey will monitor not just the Milky Way and Magellanic Clouds, but also distant galaxies, searching for lensing of background quasars and supernova. If primordial black holes lens light, Rubin will catch them. The Einstein Telescope and Cosmic Explorer represent the next generation of gravitational wave detectors. These facilities, planned for the late 2020s and 2030s, will be vastly more sensitive than LIGO and Virgo, detecting black hole mergers at all redshifts back to the cosmic dawn. They'll measure gravitational wave signals with such precision that subtle deviations from general relativity predictions, if they exist, will become apparent. For primordial black holes, this means distinguishing their mergers from stellar black hole mergers through spin measurements, mass distributions, and merger rates as a function of cosmic time. If primordial black holes merge more frequently in the early universe, these detectors will see it clearly. The Square Kilometre Array, a radio telescope network spanning continents, will probe the universe at frequencies inaccessible to current instruments. Its primary science goals include mapping the 21-centimeter signal from neutral hydrogen during reionization, studying pulses with microsecond timing precision, and detecting transient radio sources. For primordial black holes, SKA offers multiple detection pathways. The 21-centimeter observations will reveal whether primordial black holes contributed to reionization through their accretion signatures. Pulsar timing will detect gravitational waves from supermassive black hole mergers, potentially revealing whether these giants grew from primordial seeds. Transient radio surveys might catch emissions from primordial black holes accreting gas in the intergalactic medium. The James Webb Space Telescope, already operational, continues to push observational limits on the early universe. Its infrared capabilities allow it to see the first galaxies forming in the cosmic dawn, many appearing more massive and mature than models predict. If primordial black holes seeded these early galaxies, JWST's observations will provide indirect evidence through the timing and properties of early structure formation. The telescope can also search for intermediate mass black holes in nearby galaxies, looking for accretion signatures or dynamical effects on surrounding stars. Each discovery refines our understanding of how black holes of all masses fit into cosmic history. Particle physics experiments are also evolving. The High Luminosity Large Hadron Collider, an upgrade to CERN's flagship facility, will collide particles at unprecedented rates, generating massive datasets for searching for new physics. While it can't create primordial black holes, the energies are far too low. The precision of its measurements could detect passing primordial black holes through gravitational perturbations of particle beams. Similarly, next-generation neutrino detectors like DUNE and Hyperkamiokande, with their enormous volumes of ultra-pure water or liquid argon, might catch transient gravitational signals from black holes passing through or near the detectors. Atomic clock networks are becoming more sophisticated and widely distributed. The International Atomic Time System, GPS satellite constellations, and dedicated timing experiments all maintain ensembles of atomic clocks with nanosecond synchronization. Future quantum clock networks using optical lattice clocks that are even more precise will form a global gravitational wave detector sensitive to frequencies complementary to LIGO and LISA. Primordial black holes passing through the solar system would create timing glitches across the network, detectable through careful analysis of clock comparisons. Gamma-ray observatories continue to scan the sky for transient bursts. The Fermi Gamma-ray Space Telescope has operated for over a decade, building a catalogue of thousands of bursts from various astrophysical sources. None have been definitively linked to evaporating primordial black holes, but the search continues. Future gamma-ray missions with improved energy resolution and timing capabilities will refine the search, looking for the specific spectral signatures Hawking radiation would produce. Even a single detection would revolutionize our understanding of black holes and quantum gravity. Ground-based observatories are also advancing. The extremely large telescope, under construction in Chile, will be the largest optical telescope ever built, with a 39-meter mirror. Its adaptive optics system will resolve structures smaller than what Hubble can achieve, allowing detailed studies of galactic centers, star clusters, and the immediate environments around supermassive black holes. If intermediate mass black holes, potentially primordial, exist in these regions, the ELT will find them through their gravitational effects on surrounding stars. Computational advances are equally important. The next generation of supercomputers will run simulations of cosmic structure formation with unprecedented resolution, modeling how primordial black holes would affect galaxy formation, star formation, and the distribution of dark matter. These simulations will make precise predictions that can be tested against observations. Machine learning algorithms will sift through the petabytes of data from surveys like Rubin and Roman, identifying patterns and anomalies that human analysts might miss. The combination of better data and better analysis tools dramatically increases the chances of detection. The next 2 decades will be decisive. Either primordial black holes will be detected through one or more of these methods, confirming their existence and revealing their properties, or the constraints will become so tight that the hypothesis becomes untenable. The mass ranges where they could hide will shrink to narrow windows, requiring increasingly contrived formation mechanisms and distributions to remain viable. At some point, the community will reach a consensus. Either primordial black holes are real, and we found them, or they're not, and we need to look elsewhere for answers to dark matter, supermassive black hole formation, and the other mysteries they were invoked to solve. The stakes are high. Primordial black holes represent a direct connection between the Big Bang and the present universe, between quantum fluctuations and cosmic structure, between the smallest and largest scales of physics. Finding them would validate entire frameworks of cosmology and inflation theory. What primordial black holes tell us about the universe's beginning? If primordial black holes exist, they're more than just exotic objects scattered through space. They're fossils from the universe's first moments, frozen records of conditions when the cosmos was younger than a second old. Every primordial black hole encodes information about the Big Bang, about inflation, about the physics governing the earliest epochs. Detecting them and measuring their properties would be like opening a time capsule from the dawn of creation, revealing secrets about how the universe began and why it has the structure we observe. The mass spectrum of primordial black holes maps directly onto the history of the early universe. Each mass corresponds to a specific moment when conditions allowed gravitational collapse. A black hole with the mass of an asteroid formed when the universe was about a microsecond old during the quark-gluon plasma era. A solar mass black hole formed around 1 second when neutrons and protons were just beginning to bind into nuclei. 1,000 solar mass black hole formed later still, perhaps during the transition from radiation domination to matter domination. By measuring how many primordial black holes exist at each mass, we reconstruct the timeline of density fluctuations in the early universe. This timeline tells us about inflation. The inflaton field, driving the exponential expansion, had a potential energy landscape that determined how fluctuations grew. If that landscape was perfectly smooth, fluctuations would be nearly scale invariant, and primordial black holes would be rare. If the landscape had features, bumps, valleys, plateaus, fluctuations would be amplified at specific scales, producing spikes in the primordial black hole mass spectrum. Measuring those spikes reveals the shape of the inflaton potential, constraining which inflation models are correct and which can be ruled out. The abundance of primordial black holes also constrains the energy scale of inflation. Inflation happened at energies far beyond what particle accelerators can reach, possibly approaching the Planck scale, where quantum gravity effects become important. The amplitude of density fluctuations depends on this energy scale. Too high, and fluctuations are so large they'd form black holes everywhere, overproducing them beyond observational limits. Too low, and fluctuations are too small to make black holes at all. The observed abundance, or lack thereof, pins down the energy scale, connecting observations of primordial black holes to fundamental questions about the forces and particles at work during inflation. Primordial black holes also test the physics of phase transitions. As the universe cooled from the extreme temperatures of the Big Bang, it underwent several phase transitions, moments when the vacuum state of fields changed, releasing energy and potentially creating topological defects. The electroweak phase transition, the QCD phase transition, and possibly others left imprints on the universe. If any of these transitions were violent enough, they could create primordial black holes through bubble collisions or enhanced density fluctuations. The mass distribution of primordial black holes would reflect which transitions occurred and how energetic they were. The formation mechanism itself provides insights into quantum gravity. When a primordial black hole forms, it's not from a collapsing star with well-understood physics. It's from a pure gravitational collapse in a quantum environment where space-time itself is fluctuating. The boundary between classical and quantum breaks down. Understanding this process requires knowing how quantum mechanics and general relativity mesh, the holy grail of theoretical physics. Primordial black holes are natural laboratories where this meshing happened in real cosmic conditions, not idealized thought experiments. If primordial black holes contribute significantly to dark matter, it changes our understanding of structure formation. In standard models, dark matter is cold and collisionless, smoothly clustering under gravity to form the scaffolding for galaxies. Primordial black holes are different. They're point masses, clustering more aggressively and interacting through dynamical friction. Simulations show that structure formation with primordial black hole dark matter proceeds differently, with more early clustering, more massive early galaxies, and different patterns in the cosmic web. Observations testing these predictions directly probe the nature of dark matter, resolving one of cosmology's greatest mysteries. The spins of primordial black holes carry information too. When they form from collapsing overdensities, the angular momentum of the region determines the black hole's spin. If the early universe had large-scale rotation or vorticity, perhaps from turbulence during inflation, primordial black holes would inherit that rotation, showing correlated spins across the sky. Measuring spin distributions from gravitational wave detections could reveal whether such large-scale motions existed, constraints that are impossible to obtain any other way, since all other traces have been erased by cosmic expansion. Primordial black holes also connect to the multiverse. In eternal inflation, our universe is one bubble among infinitely many, each with potentially different physical constants and histories. The formation of primordial black holes depends on local conditions during inflation in our bubble. Their abundance and properties tell us where our bubble sits in the landscape of possibilities, whether we're in a typical region where inflation was smooth or an atypical region where it was violent and fluctuation-rich. This anthropic information constrains which kinds of universes can support observers like us. The survival of primordial black holes over cosmic time is itself informative. Black holes lighter than a certain mass evaporate through Hawking radiation, and the fact that we don't detect explosions from evaporating black holes sets limits on how many light ones formed. But it also confirms Hawking radiation, one of the most important predictions linking quantum mechanics to black holes. Finding an evaporating primordial black hole would be the first direct test of Hawking's theory, probing quantum field theory in curved spacetime under real conditions. If no primordial black holes are found despite increasingly sensitive searches, that's informative too. It means inflation was smoother than many models predict, that density fluctuations never reached the threshold for black hole formation in significant numbers. This constrains the inflaton potential to be simpler, less featured, ruling out complex scenarios invoked to explain other phenomena. It also means dark matter is almost certainly particle-based, focusing the search on axions, sterile neutrinos, or other exotic particles. Either way, the answer advances our knowledge. Primordial black holes tie together themes across all of physics: gravity, quantum mechanics, cosmology, particle physics, thermodynamics. They're predictions of general relativity operating under extreme conditions, signatures of quantum fluctuations amplified to cosmic scales, fossils from the Big Bang, potential constituents of dark matter, seeds of galaxies, and laboratories for quantum gravity. Few objects in physics connect so many disparate fields. That's why they're compelling, why researchers keep searching despite decades without definitive detection, and why finding them or ruling them out matters so much. The universe's beginning is written in many places, but nowhere more directly than in primordial black holes, if they exist. At the threshold of discovery. The universe is far stranger than we ever imagined. In the first second after the Big Bang, conditions so extreme existed that black holes could freeze out of pure space-time, born not from dying stars, but from the violence of creation itself. These primordial black holes, if they exist, connect the smallest quantum fluctuations to the largest structures in the cosmos, threading through cosmic history from the first instant to the present day. They might be dark matter, hiding in plain sight for billions of years. They might seed supermassive black holes, explaining how galactic giants grew impossibly fast. They might be utterly absent, a beautiful idea that nature chose not to implement. We stand at a threshold. The next generation of instruments, gravitational wave detectors, telescopes, gravitational lensing surveys, will either find primordial black holes or constrain their properties so tightly that only narrow refuges remain. Either answer transforms our understanding. Discovery would validate entire frameworks of cosmology, revealing the texture of inflation and the dynamics of the early universe. Absence would sharpen our search elsewhere, forcing new ideas about dark matter and structure formation. The coming decades will tell the story, one detection or constraint at a time, until primordial black holes emerge from hypothesis into reality or fade into the footnotes of theories that didn't quite work. Whatever the outcome, the search itself pushes the boundaries of what we know, reminding us that the universe's deepest secrets might be hidden not in distant galaxies, but in the very first moments after everything began.